Good morning, everyone. Or I should say also good afternoon and good evening, depending on where you are in the world. Welcome to ICDE 2020, the first ever virtual ICDE conference. I'm the General Co-Chair, Bhavani Thuraisingam, and I welcome you together with my co-chairs, Elena Ferrari and Rao Kotagiri. So the evolution of ICDE 2020. Since its inception, and that was 36 years ago in 1984, the ICDE conference has become a premier forum for the exchange and dissemination of data management research among researchers, practitioners, developers, educators, and users. So we wanted to continue along with this tradition and host 36th ICDE in Dallas, Texas, in person from April 20th to 24th, 2020. Unfortunately, we had the world pandemic, COVID-19. And therefore, it's extremely unfortunate that we are unable to host this very prestigious event face-to-face. Nevertheless, the very hard work of the entire organizing committee, the IEEE Computer Society, the ICDE Steering Committee, and the ICDE Technical Committee, and also the authors and presenters and our student volunteers, we have been able to put together all parts of the conference and host this event virtually. And as I said, the first time in the history of ICDE. So we will be holding all the events online, April 20th through 24th, and that's USA Central Daylight Time, which is also Dallas, Texas time. We welcome you to this virtual meeting, ICDE 2020. So we have a very exciting program that's lasting 5 days. Yesterday, April 20th, we had the workshops and they were very successful. And today we start the main conference, and we'll be having this conference for 3 days, Tuesday, Wednesday, and Thursday. And April 24th, that's Friday, we will be having the Women in Data Science Day. And that is called WIDS, Women in Data Science, as an ambassador to Stanford University's WIDS. It's taken the entire world to make ICDE 2020 happen. And there are many people I have to thank. Our research program chairs, Dimitrios Gounopoulos, Murat Kantajulu, and S. Sudarshan, they worked really hard, night and day, to make this conference happen, and I thank them. I also have to thank many others, our industry program chairs, Surajit Chowdhury, LV Venkat Subramaniam, Jingren Zhao, workshop chairs, Chris Clifton, Mohammed Mokbel, panel chairs, Meikang Chiu, Anna Scutiarini, tutorial chairs, Jayant Haritsa, Bana Kalagoraki, TKDE poster chairs, Bin Kui, Donatella Famani, Latifa Khan, demo chairs, Junet Akora, Angela Bonifati, Dacheng Chatau, PhD symposium chairs, Feng Chen, Latifa Khan, Jeffrey Zhu Yu, finance chair, Yan Huang, sponsorship chairs, Lei Chen, Selchuk Jandan, and Sharan Merotra, publication chairs, Shushin Chen, Karuna Joshi, publicity chairs, Li Jun Chang, Mohammad Al Hassan, and Bin Yang. And all those local to Dallas, registration chair, Wei Li Wu, Women in Data Science Day chairs, Latifa Khan, and myself our web chair, Aparna Srivastava, and our local arrangements chair, Rhonda Walls. Rhonda kept the entire conference together. She was central to the conference and worked with our program, especially our research program chairs, and they did a really great job in making this conference happen. As I said, it took the world to make ICD 2020 happen. We have to also thank many others, IEEE Computer Society, ICDE Steering Committee and ICDE Technical Committee, our session chairs, and all our student volunteers, and of course the authors and presenters and all of you, the attendees. And as I said, special thanks to Ms. Rhonda Walls, who was central to organizing this conference. And we would like to thank our sponsors for staying with us, because it was really a difficult situation, because when we found that we could not have an in-person ICDE in Dallas, Texas, we first wanted to postpone to the fall, but we didn't know what the situation would be in the fall. Then we decided, yes, we will go ahead and have this conference. So our sponsors, if we had had this conference in person, the sponsors would have been here in Dallas to meet with all the participants, and unfortunately they were unable to do that. So we had the Alibaba Group, Qatar Computing Research Institute, 2 Sigma, UT Dallas. We thank all of them for staying with us. And then of course the Data Engineering Technical Committee and the IEEE Computer Society. However, what we have been able to do is, for our gold and platinum sponsors, we've been able to organize some presentations given by them at ICDE 2020 before and after the conference days. So our gold sponsors, Alibaba, will be going tomorrow, Wednesday morning, April 22nd, from 7 to 8 a.m. Central Daylight Time, the United States Central Daylight Time. And the Qatar Computing Research Institute will be giving their presentation April 23rd, that's Thursday, from 7 to 8 a.m. Central Daylight Time. And our platinum sponsor, the University of Texas at Dallas, they will be giving their presentation Wednesday, April 22nd, that's tomorrow, from 4 to 5 p.m. Central Daylight Time. So please make note of it. And this is going to be before the conference starts and then after the conference ends in the evening. So once again, I welcome you to ICDE 2020, and I really hope you enjoy this conference. And at this time, I would like to turn it over to the program co-chair, the research program co-chair, S. Sudarshan, to give you some information about the technical program. Thank you.
Thank you, Bhavan.
Welcome, everyone. And thank you very much, Bhavani, for a nice summary of what has happened so far in terms of organizing the conference. I'm now going to go into a little more detail on the program committee, the research track in particular side of things. So I'm presenting this talk on behalf of myself, Sudarshan from IIT Bombay, and my PC co-chairs, Dimitrios Gunopoulos from the University of Athens and Murat Kantashioglu from the University of Texas, Dallas. So the research track had a huge number of people contributing in terms of evaluating the papers. We had 24 vice chairs, and there is a list which you see on the screen. It's a little too long for me to read out individually, but every one of them has contributed a lot, spent a lot of time on figuring out which papers should be in and which should be out, based on the reviews of 211 PC members. And that list is even longer. There's no way I can even show it on a single screen. You will note that the vice chairs are from all over the world, as also our PC members. So this pie chart here tells you where our PC members are from. You'll note that about 1/4 are from the United States, about 11 and odd % are from China, and then there's a distribution amongst many other countries, including Hong Kong, Australia, Germany, UK, and so forth. So it's a truly international program committee. Now, we are not able to individually thank each of the PC members. However, there have been a lot of PC members who have taken extra interest and given very good reviews for papers. And to recognize these PC members, we had a system of reviewer rating done by vice chairs. And we took the reviewers with the highest average rating and cross-checked their reviews to make sure that there were no glitches in the ratings. And in fact, there were no issues. And the winners of the Outstanding Reviewer Award, you can see their faces here. And if you want to know their names, which I'm sure you do, here they are. We have Umar Farooq Minhas from Microsoft, Ismail Ukid from Snowflake, Gabriel Ginita from UMass Boston, Werner Nutt from Free University Bozen Bolzano, Costas Zumpatianos from Harvard, Aibo Hu from Hong Kong Poly, and Sven Helmer from the University of Zurich. Of course, these are not the only ones who did excellent reviews. We were not able to name and thank and give awards to everyone who contributed. But there were many others, and we are very happy with the fact that many reviewers who we could not give the award to also had very high ratings. Now, here's the part which authors are always most interested in, which is the paper submission and acceptance rates. So this year we had 568 papers after DEST rejects of submissions which were not complete. And these were divided in two submissions. And the first round had 273 and the second round had 275. So roughly evenly distributed across the two rounds. And out of these, we had full accepts for 129 papers, or 22.7% accept rate. Again, these were divided amongst the two rounds as 63 and 66 papers, so it's roughly balanced in terms of acceptance rates in each of the two rounds. In addition to the full accepts, we had a number of papers which were accepted as short papers or poster papers, and there were a total of 55 such papers for 9.6% accept rate over and above the 22. And again, these were roughly evenly distributed across the two rounds. So ICD continues to be a fairly selective conference, and we are happy that we have very good submissions. The number of submissions has probably increased a little bit from past years, although it's not drastically different. We also had the statistics for the other tracks here. In the demonstration track, 16 out of 39 submissions were accepted for 41%. In the industry track, 15 out of 57 were accepted. So we have 26% acceptance. We have 6 out of 10 tutorials, 14 out of 17 TKD posters, and 7 out of 9 submissions with PhD symposium accepted. Now, the TKD posters are basically extended abstracts of papers already published in TKD, which were not published at any conference earlier. So they get a chance to present at the conference. So in addition to an extended abstract in the proceedings, they will also have posters. And I'll tell you more about that in a minute. So here is statistics about the submissions and decisions by area. Now, these are broad areas which we used to tag, authors used to tag papers when they submitted them. And as you can see, data mining and knowledge discovery has by far the largest number of submissions at about 140. And a decent number of them were accepted either as full or as poster. And if you go down the list here, we have graphs, we have temporal, spatial, mobile data, we have query processing and optimization, database privacy, security, data science, distributed parallel and P2P data management, and so forth, all of which had a good number of submissions. And then there's a further long tail over there. Now this slide actually does show you the accept and poster percentages, but to make that more clear, we have a slide here which shows the acceptance rates by area. And if you see, the top acceptance rate is by modern hardware and in-memory database systems. This tells you something about what is happening in the field. There's been a lot of change in hardware in the last 5 to 10 years, and this is reflected in a lot of interesting papers coming out, and correspondingly, they're seeing a good percentage of accepts. Similarly, we have database technology for machine learning, that's a hot area, and machine learning for database systems. Both are very important today, and you can see that they have high accept rates. And high accept rates are also there in several other areas: strings, text, query languages, distributed parallel management, but some of these are on much smaller number of papers. Now here's another bit of statistic, which is where did the papers come from? And these statistics are based on the country of author as recorded on CMT of the contact author. So you'll notice that China has by far the largest percentage of papers at about 40%, and then comes United States at 16.6%, and then a variety of other countries, including Hong Kong, Germany, Australia, Korea, and so forth. And here is another way of looking at the statistics, this time not by submissions, but by number of papers plus posters accepted by country. And here you'll see that China again has the largest number of papers at over 60, and US comes next at nearly 40, 35 or so papers. And then again, there are a number of other countries, including Australia, Singapore, Denmark, Germany, and many others. I would like to now move on to an important part of this talk, which is the ICD 2020 Best Paper Award. Before announcing the awards, let me tell you about the process. Each paper could be nominated by the reviewers and the vice chairs who manage that paper for the Best Paper Award. They had a checkbox to nominate it. Now we've looked at these nominations, papers which had at least one nomination, and selected the highest ranked ones from amongst these. And about 6 papers were selected, and we constituted a Best Paper Award committee which had 4 of our vice chairs, Jonathan Gorsim, Nikos Mamoulis, Srini Pathasathy, and Ken Ross. Each of them was given these papers, each of them independently ranked the papers. Now in most cases, there is some disagreement and discussion in order to decide which is the best paper. But interestingly, in this case, all 4 ranked one paper as the top paper, and so the choice was unanimous. Let's say something about the paper. And that paper, the winner of the ICD 2020 Best Paper Award, is Efficient Query Processing with Optimistically Compressed Hash Tables and Strings in the USSR. And this is by Tim Gubner, Victor Leis, and Peter Bonks, who are from CWI and the University of Jena. Congratulations, Tim, Victor, and Peter. They have won many awards for other papers, and this is one more in their stack of awards. And please note that this paper will be presented later today in the research session 06 on Query Processing 1, which is from 1:30 to 3 p.m. today. Now, I want to say a bit more about the online program. We have a very exciting program ahead. We have a number of synchronous sessions, including 4 keynotes, one of which is coming up just after my presentation. We have 27 research sessions, 6 tutorials. I want to note that one of the 6 tutorials selected earlier withdrew at the last minute, but we had a bunch of authors of another tutorial who were willing to pitch in at the last minute. So tutorial 2 is on fairness in rankings and recommenders, and you will find more details on the program page. We have 3 industry sessions, 2 PhD sessions, and all of these sessions are 6-way parallel. It's more than what we initially planned, but we decided to do this so that the day will end early. There are people from the Far East who are staying up late already, and we wanted to not stretch their staying up more than what we could manage. So each day typically ends by around 2:30 to 3:30 p.m. We also have asynchronous sessions for the posters, demonstrations, and the TKD posters. It was not possible to have live presentations for all of them. In a normal conference, these posters are in a single session. You can walk around, browse posters, or view demos. Here too, you can do that, except virtually. You can view their videos as well as their presentations online. It's all linked from the conference webpage, which is available to registered participants. So please go through, browse. And if you have feedback or questions, there are ways to do that asynchronously. So please use it. The authors will really appreciate getting your feedback, and I'm sure they will reply to your questions. So all the online program details are available on the password protected site. You should have already got this with your registration email, and I assume that you opened this page and that's how you got a link to this Zoom session, which you are now attending. If anyone asks you how to do this, you can share the details with them if they have already registered. We have the Zoom number of registration limitations. We are not at the limit, but we would appreciate if you shared it only with registered participants. Now, the video talks for all asynchronous sessions are already available, as I told you. And for synchronous sessions, we will share it later, after the session, now, hopefully by the next day, but if not, soon after. Now, we are using Zoom for all live sessions. As you would have seen, participants are muted for this webinar session in particular. Please use Slack or chat to ask questions, and session chairs will pass on selected questions to the speakers. And also use Slack for all asynchronous interaction. Now, you'll see Slack links. If you click on them, if you have not already registered for the IEEE ICD 2020 Slack workgroup, you will not be able to see the Slack channels. So please first click on the link which is available on the password protected site to join the Slack workgroup, and only then click on the Slack links. So I also want to tell you a bit about what happened from the back end over the last few weeks. We had a very limited time to go online after the IEEE transaction. The Technical Committee on Data Engineering made a decision to take the conference online, as opposed to what it was thinking earlier about postponing. Once it became clear that postponing would not be useful. So the time was very short, but we decided it made sense to do it as per the scheduled dates. And with help from all of you, we could make it happen. In particular, we want to thank the authors and the speakers who all scrambled to put together your talks. In particular, the tutorial speakers had much longer talks to put together. We also like to thank the organizing committee members who scrambled to make these things happen, and all the student volunteers. There's a lot of other back-end work. We had to collect and organize videos, presentation, and so on, which doesn't usually happen in an offline conference. And Google Sheets and Forms plus Microsoft CMT saved the day. As part of this, we also learned a lot about how to manage Google Sheets, including my favorite, the VLOOKUP function to look up things from across sheets. So what we realized at this point is that we are really running a whole database application from within a spreadsheet. So we can make it happen, but it would be nice if somebody takes this up and treats it more as a database viewpoint rather than a spreadsheet viewpoint, which would make life easier for putting these sort of things together. We also had to learn how to run a conference on Zoom. Most of us had probably never used Zoom before. And we'd like to thank the IEEE team, Patrick Kellenberger and Steve Woods, who had training sessions and supported us. Now, all this work, we hope would have a very good payoff. And in fact, we have 2,000 registered participants, which is about 3 to 4 times the number of registrants in previous years. So it'll be nice to reach out to a much larger audience than we normally do. We hope you have a very good online experience. So we hope you enjoy the conference. We will soon have the first keynote talk by Johannes, but we have time for a few questions about the conference before we move on to Johannes. Please feel free to use chat to ask questions.
Ralph raised his hand to ask a question, I guess.
Yes, it looks like we have one person who raised the hand that he has a question. 2 participants have raised hands.
Yeah, whoever raised hands, we request you to type your question in the chat, so we can see it.
Or use Q&A. The Q&A button should also be available there.
There's also a question and answer button. You can ask your questions.
Eric Neuhold has a question. I'm going to, where did Eric go? Okay, there's a question from Inamul Haq. It says there are many research grad students who cannot attend because of the fund availability or paper publication. Can you keep at least 1 or 2 sessions free online every year? I think that's a nice suggestion. Maybe some of the keynotes, maybe if not online, they should be made available after the conference. And in fact, we will be doing it this year. Right now, these talks are all available only to registered participants, but we are going to make them available through 2 means. There will be a YouTube channel which will have it long term, but we also have a company called VideoKen, which is organizing these talks in an interesting way with features to search in the text which is there within the talks and to browse these talks. So we will be putting up a link to that as these talks come online. So please do encourage all your students who did not register in time to do this for this conference. And even if they registered, if the talks were at timings which were in the middle of the night, they can still see this.
Right. I would also like to add, as Sudarshan mentioned, yes, all of these presentations, the video presentations will be on the YouTube channel under ICDE, as well as the video links. So we will inform all the conference attendees by email when these channels, when these video presentations are ready.
We have time for maybe another 1 question before we start the next session.
Also, I think Eric Neuhold wanted to say something. I think you can talk now.
Okay, hello. The TC chair of TCDE, and I actually want to thank all these people that have made this virtual conference happen. It was only 2 weeks' time since we decided to make it virtual, and I understand this tremendous effort to make this a beautiful conference. So I really want to thank, in the name of all the TCDE members, and maybe also future members that will join us, to the whole committee and everybody involved. Thank you very much.
Thank you, Eric.
Well, thank you very much.
Thank you.
And also keep in mind what we just said. I mean, maybe this is a good opportunity to have more people being able to attend these conferences for free or wireless or online and so on. You know, it's an experiment.
Yes,
and let's see how it goes.
Yeah, we are happy that so many people have signed up now. This was the whole idea of making it free for everybody, and maybe they will get a taste to have the physical conference next year and join us then in probably, I think it will be in Greece, if I'm correct. Okay, thank you very much.
Thank you.
Okay, at this point, it's time for the next session. If we have Johannes online. Johannes, you can start your screen share.
Okay.
And that will replace my screen, and then I'll, once your share starts, I'll introduce you.
Yep. Is this working? I cannot start a video.
Yeah.
The host has stopped it. It says that again, but otherwise, can you see my screen?
Yes.
Yes.
Okay, perfect.
See your screen.
That's great.
Great. So let's get started with this session. I'm chairing this session, and I'd like to warmly welcome Johannes Gerke, who is going to be delivering the first keynote talk of ICD 2020. Johannes is a technical fellow at Microsoft, where he is leading architecture and machine learning in the intelligent communication and conversations cloud, which is a lot about what this conference is, I think, but he will tell us more about it in his keynote talk, which we are looking forward to hearing. Johannes did his PhD from the University of Wisconsin-Madison in 1999, and from then till 2015, he was in the faculty of the Department of Computer Science at Cornell University. And then via a startup, he eventually joined Microsoft, where he decided to do more applied research, and the fruits of that are going to impact us in very interesting ways, which he'll be telling us about. Johannes has received numerous awards through his career, including an NSF Career Award, a Sloan Research Fellowship, a Humboldt Research Fellowship, the 2011 IEEE Computer Society Technical Achievement Award, and he is an ACM Fellow. He's also a co-author of the undergrad textbook Database Management Systems with Raghu Ramakrishnan, which is currently in its third edition. It's called the Cow Book. And he was program chair of a number of leading conferences, including ICD itself, KDD, VLDB, and SOC. So Johannes, over to you.
Okay, thank you. Can you hear me?
Yes, please go ahead.
Okay, I have quite a bit of echo here, but maybe that'll go away. So I want to start right away with sort of the context of the talk, namely that right now I'm at Microsoft and I work in Office 365, which is one of the largest collaboration clouds. We have over 180 million active Office users. There are a billion meetings set up each month, like this one. Billions of documents are created each month. And so what I'm working at is actually called Microsoft Teams. It basically has three different goals. One of them is to connect the dots, that basically good teams, they just don't meet for the sake of a meeting. A good meeting usually involves upfront prep and post-meeting follow-through, and the data is in silos and across apps, and Teams brings all of this together. The second one is that Teams is really focusing on inclusivity, inclusiveness, namely there's a diverse global workforce from lots of different generations with different expectations. And basically, Teams includes features where everyone's voice is heard, regardless on where they are and the level of technology proficiency. And the last one is that as teams and projects go larger and more dynamic, we need to evolve the organizational culture towards transparency. And so therefore, we need to redesign the tools just to bring everything together. So these are the three tenets. And Teams also includes voice and video calling, similar to Zoom, what we're using right now here. I just want to show a few features, and that'll bring me sort of to the main part of my talk. So here's an example of audio and how we actually do crystal clear audio and ultra low bandwidth.
The coffee stand is too high for the couch. The coffee stand is too high for the couch.
So I hope that you hear the difference between the two. Similarly, when you work in noisy environments and in open space, we can eliminate background noise. Here's an example. And now the noise suppression is taken on. And the that very often we have meetings where a few people join remotely, and then there's a heated discussion. You've probably seen this with with PhD students and colleagues, right? And then you go into the whiteboard, but some people are remote. So and then now somebody takes out their cell phone to take pictures and share them. And so what we basically have is we have created, in collaboration with MSR, we have basically the idea that you can make the picture work with real-time streaming. And so we added deep learning segmentation to filter out the person who's blocking the whiteboard. And the result is what you see at the bottom right, which is basically an enhanced whiteboard view for remote people in real time. We cannot really completely look through the person yet, as you've seen it, but we're working on that as well. So let me go on and actually talk a little bit about resource management in Teams. So, and I'll make the connection to database systems in a minute. So if you look at resource management in these applications, it's quite complex because it has to work over various networks, 2G, 3G, LTE, wireless LAN, and so on. Lots of different platforms, lots of different hardware with different capabilities and power conditions. And what our engineers have done over the years is they've identified several hero conditions and have done hand-tuned parameter tuning for video resources, audio jitter control, bandwidth estimation, and so on. So if you look at the overall high-level architecture, there's basically the capture, encoding and sending, and the receiving and decoding, and that's the data plane. And then there's basically a control plane, which controls capture rate controller, quality controller, and bandwidth estimation at the very highest level. And so the journey that we're on right now is that we're taking these 150,000 lines of code for the red blocks, which is basically a decade of hand-tuned parameters, really thoughtfully done, very often by teams that have done very careful experiments. And what we're trying to do is now we're taking all of these red pieces, basically the control plane, and replacing it with machine learned control. And maybe what we can do we might as well, hopefully, or at some point in future time, maybe replace also really large parts of the data plane with machine learned control, or with the machine learning model. So let's compare these two different approaches, right? On the left-hand side, you have the traditional approach, right, where you basically have lots of code, hand-tuned parameters. The interesting thing is that all the learning here and the expertise is done by developers who add new code and new rules. This requires networking coding experts that have a steep ramp-up time. There are people who have PhDs and who are really experts in this area. And then we have new network and device support. It basically needs somebody to go ahead and write more code. On the right-hand side, potentially, you have a simpler architecture. Many fewer lines of code, no hand-tuned parameters, no hand-coded rules. Everything is automatically learned from data. And we have, though, now very different expertise, right? We have machine learning, deep learning, and maybe reinforcement learning expertise required. And then if I now have new network and device support, I need more training data. So actually, the power is shifted away from code to the data. So here's just an example of what we can do. So again, so I've looked at sort of this whole data plane here, and let me zoom in a little bit. So previously, you start with a microphone, then you go through analog gain control, echo cancellation, noise suppression, voice activity detection, key tap suppression, digital gain control, and then howling suppression, or suppression, and then what we're doing is we can take these three red boxes and compress them into one green box, where the green box is a model. Let me just show you a little bit of the kind of quality that we can generate. So this is babble noise. So here's an example of what this babble noise creates.
Your curiosity went happily out of bounds.
So this is the noisy data. Then with existing tech,
your curiosity went happily out of bounds.
So the babble noise in the background is a little bit gone, but if we actually now have a deep model,
your curiosity went happily out of bounds.
You see that the noise is completely gone. And you probably have been in a meeting where it's joined remotely and somebody has been eating.
Eternity is no time for recriminations.
And with existing tech again.
Eternity is no time for recriminations.
The munching noise is basically not gone at all.
Eternity is no time for recriminations.
With the deep net, we can basically completely eliminate background noise completely. And in a situation like now where everybody is working remotely and have children at home, pets and other activities at home, this is a really great capability.
Your curiosity.
So another example that we actually have seen and that I was very intimately involved with as well is actually where I've seen this power of data and models in enterprise search. So if you go 15, 20 years back, right, and in VLB 2005, this is Björn Olstad, who was the CTO of FAST at that point in time. He presented basically the FAST technology, which was basically a really cool search engine, enterprise search engine based on an inverted index technology with some really cool tricks. However, enterprise search, which is basically where you have a corpus in the enterprise and you have to search over the whole corpus, has never worked as well as internet search. And there are actually structural differences. Basically in the enterprise where I have Word documents and PowerPoint documents and other documents, I don't have a link structure. I have very little information about the importance of sites. So if Sudarshan stores some documents on his OneDrive and I store some on my OneDrive, we don't know which one of these is more important. And also because the population which searches over this corpus is much smaller, They're just very few searches and clicks across the corpus. So however, if you now compare this now with the power of data, this is actually why I came to Microsoft in 2013 to build this. What we can do now is actually in the cloud with Office 365, we actually see who is working on what context and on what documents. So basically, if you look at a document to see, you can see with whom the document has been shared, in which emails the document has been attached. You can see who is colleagues of, who are the people who are working with each other. And so you can basically overlay all of these signals. They are automatically generated just by people working in the cloud across all of this content. And with this content now, you can do two things. First of all, you can now use this data-rich signals or this data asset to create new experiences. On the left-hand side is an experience that we've created. It's called Delve, which is basically a relevant feed for you. And on the right-hand side, you can also now pivot content around entities. For example, if I want to find that document that Sudarshan shared with me last week, maybe I just go to Sudarshan's Delve and there directly see it. So we have sort of these mental anchors that you can now link content around. And that's really transformed at Microsoft and everywhere how we're doing enterprise search. That basically now enterprise search has become a signal-rich environment where we now have what we originally called the Office graph, and it's now become the Microsoft graph, which basically gives signals to us and of all of our tenants to build these models and create value for our customers. Now, let's go back. Let's compare these two different models of working, right? Again, this was traditional noise suppression, which is signal processing, compared to new noise suppression, which was deep learning, as well as a traditional enterprise search with inverted indices, as compared to new enterprise search with this data-rich and models for ranking. So on the left-hand side, in Software 1.0, you program with code. On the right-hand side, you program with code, data, and models. On the left-hand side, you have domain expertise, whereas on the right side, you have ML expertise. What a programmer does on the left-hand side, they transfer expertise to code, whereas on the right-hand side, maybe you just collect data. On the left-hand side, you have code complexity. On the right-hand side, you have data plus search gives you models. Again, on the left-hand side, you design clever algorithms that you've learned in textbooks and that you've come up with. Maybe the right-hand side has all these algorithms directly in the models. And again, the left-hand side, Software 1.0, gets better with better code, whereas on the right-hand side gets better with more data and, of course, also better models. The hope on the right-hand side is that it adapts with more data and is much less hard-coded and brittle. And actually, how you work is also very different. I'll come back to this in the end, namely that on the left-hand side, you write code, whereas on the right-hand side, you design model architectures and infrastructure, and you label and collect data. And the interesting thing is, and you're seeing this now, and Sudarshan talked about the program here, where there are lots of exciting papers actually in this space in general, is that this is happening now in our area as well. This is happening in database systems and also in many other areas of computer science, systems, networking, PL, and so on. And actually, you could therefore imagine that even what we have learned about database systems over time gets less and less relevant because a lot of the things that we thought we actually did traditionally, like a query optimizer indexing and so on, are now replaced with things that actually are automatically learned from data. So where does sort of the Software 2.0 and database systems meet? And they clearly meet along many different dimensions, and I don't have time to talk about all of them here at all. There's clearly a lot of really great work of integrating machine learning into database systems. There's a lot of great work on applying machine learning to database systems. But what I want to talk about here now is the third sort of big bullet component here, which is the idea of changing parts of a database system to models. And so what I want to take now is the second third of this talk and sort of give you a little bit of an intuition of what kind of work you can do here in this area. And I would say that this area is still very much in its infancy. And I'll also point this out. And then afterwards, in the last part of the talk, I'll talk a little bit about how we actually change our way of working with respect to now actually having models in code. So this is the rest of the talk. So basically, I'll talk a little bit about this learned X in database systems, and then I'll conclude with some thoughts about how software development changes. Okay, so how does this learned X actually work, right? So basically, what you do with the learned X, the idea is, well, I just take something that I have traditional code with and I replace it with a model. I could do this in a database system in the control plane where I have lots of different choices like resource management and so on, or in the data plane where I basically directly are involved during query processing. And one thing that I've seen many times now at Microsoft is that initially models are not great, but they improve over time. And they improve as we get more data. They improve as we learn more about the usage of the models, as we build better models, just in terms of model architecture, as we build more efficient models, we quantize models and have a better understanding of quality versus resource trade-offs, but also as we learn how to deal with having models in our code. And that's a really big change that I'll talk about in a second. So I want to talk about two simple problems here, just to give you an intuition of what it means to apply or replace pieces with models here. And one of them is a physical data layout for interactive analytics. So here the problem is very simple, namely that we have this trend that there is scan-oriented data processing for large-scale analytics. So what you do is you partition data into blocks stored on disk or remote storage, and then you build some block-level small materialized aggregates such as per field min and max to see whether you can skip a block. And then you retrieve and scan and full scan blocks if they're relevant to an issued query. And there is a lot of relevant work about this. And one of the key metrics here is for a given query workload, I need to optimize the total number of blocks or tuples accessed. And the main idea is basically, well, once we have these blocks, we can assign records to blocks intelligently, and we can skip blocks when running queries. So what this means is that we now optimize the total size of blocks accessed during querying. And this is basically workload aware because we can optimize it for a given data set and query workload. And again, this is a very initial step, and hopefully this actually evolves along with the database as the database changes. And we've tried to do this in our design, even though we're not there by far. And so the desirable properties of such an assignment is that, well, the block contents can be easily described as predicates over fields. So if I have a record or if I have a query, I can easily check whether a block is relevant for this query or not. And then also completeness, namely then that I know that a block contains all the records matching a given description. And this actually has significant potential. So we have tried this out on a real data set. That was actually the motivating use case here, where the scan selectivity of a large workload is less than 0.1%, which is the theoretical lower bound. And basically, if you look at actually what is happening is that in prior work, you get about 5 or 12% scan selectivity, whereas in our solution, you go down to 0.4% and 0.2%. So, not at the theoretical lower bound, but quite close to it. And you can do the same thing actually for TBCH as well, where our solution actually improves significantly as well. So I think I want to give you an intuition of the solution, but then especially I want to tell you about the approach that we took, because I think it's an interesting approach, because in the approach, we specifically designed for the future. So we have this new learned data structure, which we call a query data routing tree. And basically, the simple idea is that this is just a decision tree, where each internal node has 2 children. Each node corresponds to basically a data subspace, and you have a cut at each node. So the root corresponds to the entire data set, and then each node cuts the data space into 2 children. So it's a simple decision tree, right? I mean, when you think about, in the last couple of decades, right, decision trees was one of the early data mining tools. So this is actually nothing else. And so basically now the leaves have a complete semantic description of conceptually this hypercube that they encompass. You can have unary cuts, and you can have categorical cuts for categorical attributes, where we have a bit vector which says which value appears on which side. Now the question is, how do you construct such a tree? And now there are different optimization methods. A simple solution would be greedy, another extreme might be dynamic programming. And there are actually lots of other possibilities out there. And one approach that we took is basically we use deep reinforcement learning. And the intuition is that actually, not that the problem right now is actually really an MDP, but actually that with changes in the database, we're actually prepared for this next step that we want to take. And we're not there at all. So basically in the greedy approach, it's basically the typical top-down decision tree construction. You begin with all the tuples in a single block. in each iteration, you split a leaf node whose size is larger than 2b, which is sort of a threshold, into 2 children nodes, and choose the cut that maximizes some metric. You can really easily see that there are cases where it's clear that you don't want to be greedy, where greedy makes the wrong choice. It's the same issue as in decision tree construction. And therefore, what we do is we want to use an alternative search procedure. Again, we use reinforcement learning, really not because this is a sequential decision process, right? So usually when you look at fields as robotics or so, they've used MDPs because, well, there's a robot and the robot needs to make a sequence of decisions as it navigates its environment. And you basically, have to make the sequence of decisions to get to the end. In here, this is not really a sequential nature of the partitioning problem, right? It's basically, there's no agent interacting with the environment. Really what we have is basically just a cost function overall, not really a reward. However, in the database system is not a static object. It's changing over time. Tables can grow and shrink. And so therefore, we are hoping that as we get to this next step, we have modeled the problem in a way such that this next step will be easy. So basically what we do is we build this learned QD tree now using deep reinforcement learning, the states right now at the hypercube, the actions, the candidate cuts that we have, and then we have the policy, which is basically a distribution over possible actions, the possible cuts that we can take. I don't want to go too much into details now here, but basically what this shows is if you have, either a denormalized TBCH, again, there's a restriction because we cannot do it yet over joins and so on. And in real life data sets, we show that, for example, if you use TBCH on distributed Spark, we actually get an overall speed of 1.6x. And if you include templates that actually scan all the data anyway, it's 2.6x. And there are some queries where you get significant speed up. And similarly, actually on a commercial database system as well. And then similarly, as I've shown on the real workload, if you just look at the logical speed up directly there, and actually we get on a commercial database system here with this workload, we get about a 400x gain compared to the baseline. There, we actually have significant improvements as well. So I just want to show this, not because this is a cool algorithm, but basically it shows that if you use the traditional methods and compare now this decision of how to partition your data through a model, you basically are now can partition data set to optimize for this given data set and workload. But also you're now actually hopefully prepared for the future. And that's actually now where there's a lot of open questions. Basically, how do we handle multiple tables? How do we handle time-based predicates? And especially how do we handle database and workload changes, which was the motivation for using reinforcement learning in the first place, right? Otherwise, I could have just built a deep model, for example, that gives me a cost function and then use any kind of other optimization algorithm. Let me give you another example. So this is an example where we use this in physical layout. Another example is in indices. And this is a paper that actually became quite well known. The case for learned index structures by Krafka et al. In Sigma 2018. The main idea is similar to this query routing tree, is that if you look at traditional index structures, such as a B-tree index or a hash map, basically what they do is they take a key and give you a position. Well, and this function from a key to position, it doesn't have to be encoded in a B-tree. It could be encoded in a model. Whether it's a deep model or not, that's not the question. And similarly in a hash map, what does a hash map do? It takes a key and takes a hash function and then gives you a location. And learned hash map, similarly, you replace that hash function with a model. And the hope is that if I have this learned index and I compare it now to a B tree, that maybe I have faster queries because the tree is more compact and I don't have to make that many comparisons, and my index size is much smaller. Okay. And so the learned index basically had this hierarchical model, which actually looks quite a bit like a B tree, where I replace the internal nodes just with models. So I have a root model, and then the model tells me to which child model I should go. I basically apply a function that gives me the index of the model at the next level, and I go to that model and then I recurse. Okay, and there were some details on how the search actually converged. And what the work by Kraft-et-al. Shows is that this gives me actually 3x faster lookups and about an order of magnitude size compression compared to B+ trees. However, the drawback is that this works only for static and read-only workloads. So the design goals now here in this space, again, are basically, let's take this initial model, which is a learned index, and which has some interesting properties, and can see how can we expand this. So again, if you take the learned index, which is, you know, a fast lookup time, unfortunately no insertion and low space usage, can we do the same thing? With lookup time, maybe we can make it a little bit faster. That's a general optimization. But how we actually can we actually make it updatable with insertions? And so basically, what we do in Alex is we basically expand RMIs with a few relatively simple ideas. And by the way, for indices, simple ideas are good because in the end, you actually have to implement this. And the simpler the index is that you have to implement, the easier it will be to implement and the fewer bugs you will have. So the main idea is that we have now variable size nodes where the size is determined by actually the data set and the distribution. So basically, if the model fits the current distribution well, then we actually have potentially very large nodes. And we have a search strategy is optimized for models, where we basically do inserts based on the model as well, and then combine with exponential search. And that gives us basically a very compact index with a nice caching behavior. Okay. Let me just give you a brief overview of how this works. So Alex is, which is in the adaptive learned index, which is the name of this index. You basically start at the root. You have again a hierarchy of models, and the higher level models fix the models at the next level. And then the leaf level model predicts the position. And at the leaf nodes, basically, one idea is just to leave gaps. You leave free spaces, which then efficiently absorbs the inserts. And you can use model-based inserts, which lead to faster lookups. And actually, this simple idea already takes you very far, because once you've built this index, you can go to the leaves. Once a leaf is full, you can potentially just double the leaf, because if the distribution has not changed, well, then maybe the model that's there at the leaf, or you can construct a new model, actually still captures the distribution. So in a way, what you do is you have an overall distribution of key values, and you basically approximate this distribution with either piecewise linear or, let's say, other functions that you have at the leaf nodes. So if you have now lookup, you just use this recursive model index to predict the location of the key in a leaf node. And then within this leaf node, you use exponential search starting at the predicted location. And then we have some tricks such that the holes don't cost you too much. If an insert is well, you use the recursive model index to predict the location where the key should be inserted in the leaf data node. If the predicted location is empty, great, you insert the key. That means actually if you ever search for that key, you actually find it really quickly as well. Otherwise, you shift the existing keys towards the closest gap. And so there are basically mechanisms to dynamically grow Alex, which says if a node becomes full, you allocate a new larger node by some expansion factor. I suggested 2, but you can pick any factor C, and you can scale or retrain the model. And if the model node maybe becomes too big or becomes too skewed, then you have to split into 2 nodes. But now you actually split downwards. And basically, the insertion algorithms combine these different splitting mechanisms with policies on when to do this. Let me just give you an intuition of how fast this actually works. So basically, if you look at Alex compared to the learned index, the model B tree, a regular B plus tree, and an adaptive radix tree, Alex actually has really good read throughput. And actually, even if you look at, so it's faster than a B tree and about 2x faster than a learned index, but even the write-heavy workload, where you now have lots of inserts, it's still about 2 to 3x faster than a B tree and 3 orders of magnitude less space for the index. An interesting factor that's happening in these learned indices, though, is that from time to time, because the index gets skewed, you may have to reorganize some pieces or some parts of the index. Basically, think of it that assume we're doing just linear functions, that the linear approximation of this density there or of the CDF is not doing that well, and you basically need to find different split points. So therefore, if you look at the insert latency, Like you see that basically the B+3 P50 as well as the P99, well, there is, you know, still some orders of magnitude different, but the you know, maximum latency of the B+3 is basically capped at about, you know, between 10 to the 4 and 10 to the 6, so about 10 to the 5 nanoseconds. As you can see that in Alex, actually, this goes quite up high. This is the one with the triangles. And the main reason is that from time to time, we actually need to take some pieces of Alex and need to completely reorganize them. So this shows that Alex actually has these latency spikes, which are not really desirable in a real system. So there's much more work to be done. So it's, you know, the open question is basically here in this whole area of learned indices is this the right approach in a way? I mean, the current indices beat baselines on all data sets that we've tried it out, but is it really simple enough? I mean, the beauty of the B+ tree is that it's super simple, that it has really nice and simple concurrency algorithms, concurrency control algorithms as well. And the question here is this actually simple enough, or can we make it even simpler? And how do we actually deal with these tail latencies and all the complexities of some of the algorithms? So as we talk about the learned X, right, I've now sort of talked about two examples of where I took existing components and replaced them with models. Now, what these models need is they often need input. And I think the design of featureization is another interesting open problem in this whole space. So for example, the models, they work over some representation of the query and the database. You know, a query or a query workload or the schema or some physical characteristics. For example, assume I have this relation, you know, these three different relations, A, B, and C. I have a simple query which selects star from A and B with a join condition and a selection condition down here. One simple way of encoding this query is basically I encode the query through a feature vector. So I basically create a feature vector where maybe my first 3 bits are the relations which appear in the query. And you can see this is actually A and B appear. My next few bits are the selection predicates that I have. And maybe what I do with the selection predicate, I encode the selection predicates by the percentage. You know, here maybe A1 less than 23 is, say, 10% of the tuples get selected, whereas I don't have a condition on A2 and B1 and B2. And then maybe I have some join predicates. And this is an example that's being used in some of the learned query optimization work. But if you look at what actually happened in text, audio, video, and many other problems that we also see that I've seen here at Microsoft, is that the best models directly work on native data. Right? It's basically, again, the search story. The search story was that we started out by indexing using inverted indices and using very simple ranking functions, just as a DM25 or the statistics. Then we had teams that built features from documents. And now we basically just take the actual documents and directly feed them into a deep net. So the best models in text, images, video, and audio work directly on native data, but they didn't start up like this. And there were lots of interesting intermediate steps, you know, K-grams and hierarchical presentations and so on. But now there exist very powerful models and one-shot learning approaches that directly work on it. So what's a good featureization of a database in a query workload that we can use for some of these learning-based approaches? Another open issue that we have, I think, in the community is this whole question of what is our infrastructure and do we have shared infrastructure? So this is a great paper that I would recommend all of you read, which is a paper by you know, Duff et al., which talks really about what's happening if you do auto-tuning in practice in a real cloud infrastructure. Basically what, and so the steps are you identify a representative workload to tune, you tune the workload to identify the best index configuration, you implement these index changes, detect regressions to the index changes, you know, you revert some of the changes potentially, and then, you know, maybe you detect if more tuning is needed due to changing workload or data. Well, this sounds all fine and nice, and especially, you know, in theory, that's very easy to do, like, you know, the auto-tuning algorithm that I gave you before, right? I mean, I can really sort of let my algorithmic creativity loose on this problem. However, if you look at how this is actually done in a large-scale cloud database system such as Azure SQL DB, you have a whole architecture that is there to collect data. It's basically, this control plane is actually the brain of the system. It's a really highly available service that manages this whole fault tolerant state machine of auto-indexing for each database. There are lots of different components, basically what this all does is that it collects data, which is then used to build models, which are then used to recommend indices. Right? And one of the core parts is this query store, which is basically a repository of query plan choices and performance, and it aids basically in performance troubleshooting and tuning. It has lots of statistics and lots of data. It captures and assists query compilation, execution history, compile time stats, and runtime stats. And so the big problem that I think that we as a community face is, where do we get these workloads and data from, right? Again, so in Azure, I have easily 1 million SQL databases. In a way, you can argue that the deep learning revolution was, partly started through the creation of ImageNet, right? Which was sort of a small research paper, but then really quickly evolved into an annual competition to see which algorithms could identify objects in these images. And this was basically, I think, really a catalyst for the AI boom that we're experiencing today. So what is sort of our ImageNet for the database community? And remember that we have great benchmarks, but they're designed for a different purpose, right? They're designed for the purpose of challenging the database infrastructure and not for the purpose of creating interesting problems for the control plane and the learning that we have to do here. As we think about structured data processing, right, there are now all these large-scale pre-trained models out there that are used for many natural language processing tasks, transformer-based models like BERT and GPT-2. And what is there for our next set of challenging benchmarks, and how do we know that they will actually generalize to the interesting cases that we see in practice? In many environments, even for our noise suppression or other, for the control plane problems that we have in Teams and Skype, we have built a gym. And a lot of advances come with, different algorithms that you can then exercise in the gym to see how they actually act with the environment. We don't have a gym for database systems, and if there's a gym, creating an index, may take you seconds or minutes. So doing a lot of experiments with this gym is going to be super expensive. So what is the right kind of gym for database systems? And then also, how do we actually create an open source infrastructure that we can all benefit from and make our models and ideas comparable? So what I'm basically a little bit worried about is that there are only a few big players that are able to innovate because we don't have a good way of sharing queries and data in a privacy preserving way. So one of the things that I've been super impressed by at Microsoft, and which impressed me again every day, is how we treat customer data. I work in the Office 365 cloud. I have never seen a single piece of customer data. I cannot even get at it. I cannot log into the machines where our services are running. So there's a really extremely high bar, or actually a gate between any developer and real customer data. So we cannot share any customer data. So how do we actually either share data in a privacy preserving way or get the workloads that people have shared so that we as a research community can innovate? And that sort of brings me to my last point that I wanted to make, namely, I think what we see in industry as well as what we also see now here in this database community is that the way we develop software is changing. Right? So I talked about the switch from software 1.0 to software 2.0. But I think what's interesting is that this is not only a change in technology, but it's especially a change in process. Right? If you look at previously how software, or today how software is being built, right? You define some tasks, design some modules, you write, reuse the code, and then you debug and release. Right? For software 2.0, this has changed significantly. Now a big step is how to collect the data and labels, how to prepare data and train the model. And these steps have changed the whole process. And actually, as we're replacing code with models, right? Think about what we actually had to do in background noise suppression, to come back to the original problem example, right? We created synthetic data and captured real data of speech plus noise. And we ground truth the data sets. We created some no reference audio quality predictor. We created a background noise gem. We did some training with the gem, and potentially some prior serving online training and A/B noise suppression. A/B test the noise suppression and then monitor and repeat. Right, so these are a lot of steps, namely exploring, defining data to be used, identifying data sources, creating, collecting data, and so on, that take a lot of time and for which the tooling that we've developed doesn't have the same level of maturity. Especially if you look at any candidate that I'm, for example, interviewing for my team, they are really excited about the training, right? Should I use ReLo? What should be the number of convolution layers? What happens if you overfit? The learning rate should be this. Should I use L1, L2 norm, or this other loss function, right? What model sizes? How should I do architecture search? What's the quantization, and et cetera, et cetera. But if you look in practice, they think actually this is what they're going to spend all their time on. But if you look in practice, actually, there's all this other stuff around that takes much more time than the middle step. Especially if you look, the middle step, it's basically differentiable. Right? So there's great methods that allow me to take the model and then make the model much, much better. What I would like to do is really, I'd like to, in some sense, differentiate across the whole data lifecycle. And so this is the last point that I want to make, right? This change in process, which I just talked about, maybe from the, actually the process is a little bit more difficult, right? It's the inner cycle where basically I work by myself, right? My machine and my code. This is maybe all what we as researchers and PhD students know and work. But the outer cycle is what allows us as Microsoft, for example, to scale to code bases where we have 1,000 developers. Right? After I am done with my little piece of code, the code goes into code review, right? Then testing. There's a continuous integration pipeline. There's release management. There's monitoring. There's issues management. There's documentation needs to be written. There's analytics over the code, and so on. Right? And so I think for software 1.0, where we have a traditional program call tree with human-generated code, I think we have pretty good tooling now where we understand both the inner loop and the outer loop. Whereas in software 2.0, where maybe I have this hybrid program tree now, right? Where basically, well, I have maybe now a module that's a neural net, maybe plus human code, or just a deep net, right? Where I have a program that may consist out of some synthesized piece of code. I have a program that constantly changes based on the data that's flowing into the program, which are the actions of humans who are interacting with it, right? We don't have such great tooling. So in a way, for software 1.0, we have managed to, in some sense, tame the complexity of software development. We've made an engineering discipline, right? We have modules, object-oriented programming, version control, interfaces, etc. And in a way, the software that we have is also immutable. And the different components, they influence each other only in very well-defined ways through interfaces and APIs. And for models, we may not have really many of these tools yet. We don't really know how models influence other models, and maybe that even happens with a human in the middle. But what is sort of this engineering side of software aligned for software 2.0? I think that's still a big problem. I don't have time to go into the details here, but let me at least give you my intuition of what I think this right-hand side could look like. Namely, for repeatability, we have maybe model pipelines and environments for freezing code, data, and parameters. For testing, we might have gems, which I already talked about, right? We might have test generation with GANs and so on. For modules and decomposition, which is really a way how we scale, programming to large teams as well. Maybe we have, pre-trained models. We have transfer for learning, and we have co-training, and maybe some of these mechanisms will help us. Debugging is actually a big issue, right? Especially in software 1.0, the two of us can look at a piece of code on the screen together, and we can debug it together. It's much harder to do in a deep net, where you sort of look at a complex architecture with lots of weights. And there's, interesting work now happening to do this. Similarly, for abstractions, right? We don't have such high-level abstractions as we have in software 1.0 yet, in software 2.0, and so on. Okay, with that, I want to stay on time. And as a summary, I think Software 2.0 is happening. It will change how we build software systems. It will change how we build database systems. I talked about some ideas that we have specifically been working on in terms of learned indices, and especially in terms of learning how to automate physical database design. But especially, I think Software 2.0 is really going to change how we're going to develop software in the future. And what this also means is for us as a community, where we at the core of all of the data, we really have an exciting future ahead with us, with lots of high impact research problems. With that, I want to share you another thing that we did in Teams.
Being both technical and creative.
So I just wanted to check in with you guys and talk about
Democracy's responding to those scandals. My apologies.
Okay, and with that, I'm happy to take any questions. Thank you very much.
Thank you very much, Johannes. That was a really interesting talk. And I think there's a lot of stuff there for PhD students to take home. And I think they would really appreciate that part of the talk also. We have time for quite a few questions now. So please use the chat or the Q&A things which are available on your Zoom screen to ask any questions. I see one question up already. Let me ask that to Johannes. The question is, what frameworks, languages, DNN, lib, etc. are you using to design and optimize the models? Are all those only for clouds, or can they be used for standalone DB systems in the local machine/data centers?
Yeah, that's a good question. So I think there are different components of this question. So let me sort of try to get to them. So first of all, I think the future database systems are all going to be in the cloud. I mean, I've seen this where, early days at Microsoft, maybe customers sort of wondering about the cloud, and now it's more like about how fast can we move to the cloud. So let me talk about cloud database systems. So the question is now, what frameworks are you using? And I'm actually quite agnostic, right? I think this is again a very rapidly evolving area. There are lots of great frameworks out there. If you go and look at any deep learning tutorial or so, you can use any of the major ones, including TensorFlow, PyTorch, whatever you have. So I think the choice of framework is much less important, I think, especially since all of them rapidly innovating, as the change in how software is developed overall. I think that's the bigger change. And by the way, I just see here a comment, why can't we see Johannes? I'm happy to turn my video on, but I can't. I don't know, Rhonda, whether you can allow me to do that again, but it says again, you cannot start your video because the host has stopped it.
Let me check.
Okay. While that is going on, anyone else who has asked questions, please go ahead and ask it on chat or on the Q&A.
There's another question on the Q&A.
Yes, there's another question.
What? Let me open that up. Yeah. So Lax says, a great talk, Johannes. Some questions. What is the impact of Software 2.0 and more specifically DBMS 2.0 on debugging and explainability? And what does all this mean for future job prospects for software engineers? Nice question.
Yeah, I think this is a great question. I think debugging explainability is a big issue. And I think that's also an area where there's a lot of research right now. How can you take one of those, and they were traditionally actually even called black box models, right? Because you didn't understand what was happening inside of the model. How do you actually explain what's happening inside of a model? And I think that's still an open research area. I think there are also lots of other interesting questions. For example, questions of bias, right? For example, if you look at this background blur, right? Is the background blur now, how well it works, the segmentation, is it biased by the training data that I have? Right? Maybe I have a lot of training data of men. Maybe I had a lot of training data of, people who are middle-aged, and therefore it doesn't work for humans that well, for the general population that well. A good example of that is I have a daughter who is now 12, and we had one of the very early Alexas. And in the very early versions of Alexa, when she was talking with Alexa, Alexa completely ignored her. It seems like the speech recognition of Alexa just didn't understand that there was a human talking to her, even though when I was talking to Alexa, she clearly understood me. So I think we'll see some of these bugs, and actually we have to be extremely mindful and thoughtful about such issues. Actually, Microsoft has a great program, both internally as well as externally, about bias and fairness in AI that I would really encourage you to look at. So within Microsoft, even we have very strong restrictions and regulations about, looking inside of training data for bias and fairness. And there's actually also tooling emerging out of Microsoft that I would encourage everybody to look at.
Lax's question vanished, but there was a second part of that question. What was that, Lax? You can type it in again since I'm not able to see the question. But meanwhile, let's move on to the next question.
Yes,
this is a question from Ilan.
Sorry, I did it. He asked, what does it all mean for the future job prospects for software engineers? So what this software 2.0 means for the future job prospects for software?
Yes, I think that's a great question. So I think what it means is that maybe the percentage of experts that we need in certain areas is shifting. Right. For example, I think you still need experts in certain areas. For example, if I look at in Teams, experts in networking, in coding, and so on. But I think maybe you now also see a larger and larger population of strong software developers who basically also have a strong ML background. It doesn't mean that these are the people who are the ML scientists, but these are people who can apply machine learning in a very thoughtful and careful way to existing problems. They either use pre-trained models, or they can take existing tooling and build new models. And I think such skills will become more and more important for all areas of computer science. Actually, if you think about, again, that's sort of part of the thesis of this talk, that the way we develop software is going to change in the future. And I think models will become much more first-class citizen in all pieces of software that we're going to develop.
So we still can't see Johannes.
Yeah, I'm trying to turn it on, but it says always, you cannot start your video because the host has stopped it. My apologies.
Can someone turn it on? Because we have 3 more questions.
I'm trying. It does not give me that ability.
Okay, we apologize for these technical
I'm very
issues.
sorry.
This is the first session, so luckily this has not been a major issue. We can continue on to the next question. There's a question by Fortis Sava, which I think Johannes has already answered, so I'll skip that. There's a question from Ilan Tolowski, which says, in your experience, what are the biggest challenges regarding managing the model lifecycle? And in your opinion, the possible solutions to some of them?
Yeah, I think one of the biggest challenges is that the whole tool chain that we have has completely changed. Right? If you think about previously, we had, we have really good tooling for code, right? We have GitHub, we have test automation, we have tools for abstraction like functions, modules, APIs, libraries. We have really tools for debugging. We have for abstractions, we have high-level languages. We can do performance tuning. We have profilers, optimizing compilers, and so on. And I think for Software 2.0, it's not clear what that tool chain is going to be yet. For example, I mean, here I could imagine that, and again, there's no tooling developing around this. That if you have a model, the model is not static. So the model basically has a life of its own. It means as new trained data comes in, the model changes. What this means is you could even imagine now very different types of attacks. Maybe you could imagine a data attack on a model where I basically feed biased training data to a model with the goal that the model actually deteriorates in the future and is not any more representative of the population that it actually needs to make a prediction over. So I think the whole tool chain, as well as everything around it that we used to have for code and that we actually, in some sense, felt like we are getting a handle on, has now changed with Software 2.0 with models.
Thanks. The next question, which I'd like to ask, is from Yujia Zhang. The question is, does the traditional complexity analysis fit the new models? How can we analyze the performance of algorithms in Software 2.0? And I think this is particularly relevant to the index question, learned indices, which
you
Right.
talked about. Yeah.
Yeah, so let me actually answer this in two different pieces, right? One piece is what does it mean to have a model in software? And actually, if you have a deep model in software, the complexity analysis is actually pretty nice, because you actually just have a fixed inference over, let's say, a deep model that you're doing, and therefore it's actually very easy to understand what the complexity of that model is. Now, with the indices right now, when you incorporate models into software, especially within performance-critical parts, you have to now worry about what's happening if the data has shifted and the model is outdated. So you basically now have to, in some sense, look into what are you doing if this data has shifted, and where do you take the time for retraining the model, right? These are sort of these performance bumps, these latency bumps that we saw in the learned indices, right? Which is not a nice behavior. And maybe one idea would be, well, maybe I treat the tree a little bit like an LSM tree, that I build one tree, I use it. At the same time, from time to time, I build another tree on the side, and then I switch atomically over, right? It's similarly like, when you look at the auto admin approach that was explained in the paper from Microsoft, right? Where basically you sort of watch and see whether anything interesting is happening. And from time to time, so you have to try to build new indices again. Right, sort of this continuous approach of retraining that you have to watch out for. I don't know whether does that answer the question.
Yushia, feel free to follow up on your question. But meanwhile, let me ask a question here.
Yeah.
Last year's ICD 2019, the 10-year Best Paper Award was for a paper which basically used ML to predict query running times. And that was certainly a very interesting paper, quite ahead of its time. But what was interesting is, in 1 year after that, in 2010, there was another paper which basically said that, look, there are a few parameters for query running which we need to learn, but it's not good to do an end-to-end prediction. All you need is to learn these parameters, and that can be learned because it's common across all queries, and then that worked better than full end-to-end ML. And this may be because the amount of training data is limited, or it takes a really long time to tune some of these parameters. So do you have any thoughts on this?
Yeah, so I feel like this is just steps in a journey, right? And especially, I think one of the biggest questions here is, and I did some experiments together with Jennifer Ortiz and Marta Balazinska, on just even trying to get a little bit of a handle on how do these different models perform. And I think one of the biggest questions that came out of that study is that, how do I know when one model actually is really much better than another model? Because every data set that we try it on has certain biases in it, has certain kind of characteristics of the distribution. So especially in our case, where we have now potentially complex joins, where we have complex table layouts, where we have multi-way joins or foreign key joins, how do we actually know that if we now replace something with a model, it really performs much better? An example is query optimizers, right? There is right now, I think, very interesting pieces of work where you basically take the query optimizer and you don't actually now decompose it necessarily into selectivity estimation and plan enumeration anymore, but you basically do everything in a single shot. Again, this is working right now for very simple queries against very simple optimizers, such as the PostgreSQL optimizer, which is really not as good as a commercial optimizer. But I think it's a super interesting piece of work and a super interesting, okay, now I can actually start my video. Thank you. And so it's a super interesting piece of work, because I think what it actually shows is that learning can do well for some certain class of queries in certain distributions. And I think what this means is now, as we get more data, as we get a better handle at all of this, things are just going to get better. I don't know whether that answers your question directly.
Yeah, I think it answers it partially, at least. Thanks.
Johannes, can I ask, just follow up to
Dimitri.
Thank you for the talk. A great talk. When you say a model, I mean, what do you mean when you say a model? Is it just a collection of parameters that we have to learn? I mean, is it a space of things that there is a very big range of what people mean when they say a model.
Yeah, and in a way, you can just say that a model is basically a function that takes some input and produces some output. And the main difference is that the model is not constructed by a human by writing code, but has been learned from data, right? And so it's like a machine learned model. Maybe I don't understand the gist of your question. Are you worrying whether the model has some randomness in it? Are you wondering about the complexity of the model? There are lots of different aspects of a model, right?
All of the above. I mean, in principle, a model could be a Turing machine.
Correct.
I mean, you have to somehow define some space with
Correct, and you're right. So I've not been very precise about this. I mean, so by models, I mean maybe the kind of models that mainly appear right now in the literature, which are, let's call it deep models, as well as maybe tree-based models such as gradient boost decision trees or so. I think those are the models that right now our community is looking at. And even with deep models, I mean, we can look at RNNs or LSTMs or so, because maybe you can think of a query plan as consisting of different steps, and so therefore maybe a model with some memory might actually have some advantages there. But I agree. I mean, I'm not talking about complete code synthesis or learning code, right? Which is another interesting direction that maybe the NIST community is starting to look at as well.
Okay, we are almost out of time, but there are a few more questions. Maybe I'll see if I can pick anyone as the last question. So there's a question from Murad Uzani, which says that as we introduce more learn text components, do we need to rebuild the different DBMSs from scratch or keep modifying the existing one? I think that's a pretty important question.
Yeah, I think that's a super interesting question. And the answer is that is probably that I don't know yet, right? For example, if you look at, so what are sort of big architectural changes in the recent history that happened on the database side, right? One of them clearly was the move to the cloud. And at the beginning, what people did is they basically just, like what everybody does, they take the existing data systems and plump them into the cloud, right? And then build a control plane to manage all these database systems. And it was only after a while that we understood, and really Aurora was the pioneer here, right? How to build database systems that separate out storage from compute and actually use some of the existing infrastructure of the cloud to generate a next generation of database systems that have much better performance, are much more cost effective, and much better scalability. Really, I think what it took me a while to appreciate about the cloud, also working at Microsoft, the cloud is not about multi-tenancy and elasticity. The cloud is about having higher living building blocks that you can build on, and therefore that accelerate your productivity significantly. And I think similarly now here, when we think about machine learning and database systems, probably the first thing will be that we take our existing database systems and replace some components, maybe selectivity estimation, maybe query optimization, clearly administration, right? Which is what everybody's doing already. And maybe then after a while, we think about, we have some realization of what this next generation database system will be. And for example, there was an interesting paper at CIDR last year, SageDB, sort of a learned database system, and there have been a few other papers around it. But still, I would say that a lot of these papers, they take still quite a traditional approach in terms of, take the red book, for example, and look at what's happening with respect to a database architecture, and just take the different blocks and replace them with learned components. So I think the big question is, what is the big architectural change? I think that we don't understand that yet enough, but I think it's probably going to come.
And let me ask, I think, the last question. So this is a question for which you can wear your professor hat, although you're not a professor anymore. The question is, what changes, if any, do you believe need to be made in CS college curriculums to prepare for software 2.0? And so this is a general question. You could answer it in the context of databases if you wish to.
Yeah, so that's a really interesting question, and especially so there is a small team of people here at Microsoft, and we're looking with actually some of our academic friends at maybe even having a Software 2.0 seminar. So I would say it's maybe too early on to understand what whether there should be a class on it or how this should be woven into the curriculum. I think most major CS programs now have woven machine learning much more, in general, dealing with data much more into the curriculum of CS education. I mean, even if you look at the general software engineer, right? The software engineer now, because they look at services, they look at exhaustive services. So the whole notion of dealing with data and analyzing data is is part of the bread and butter of a software engineer. So I think data should just play a big role in CS, computer science education. And the second one is just to get a handle at models. Right? What does it mean to build a model? How to evaluate a model? What is the data life cycle of a model? How to maintain a model? I think just even getting a handle at both of these, I think would really prepare people very well, I think, for this next step.
Sudarshan, if you permit me, I would like to ask a very quick question.
Okay, you ask the last question and then we'll wrap up.
And I think I'll try to bring in one others. So in other domains, deep learning models like image processing, etc., turn out to be brittle towards some kind of adversarial attacks. You mentioned that in your slide as well. Do you see any issue on the adversarial aspect here as well, or it's not a concern? And I would like to tie you up with the data availability issue, because for small organizations, maybe they don't have enough data to build the model to begin with, and the model can be brittle anyway. What do you think?
No, I think it's a big concern. At least, I mean, we at Microsoft are super serious about this, not only about data attacks, also about fairness and bias and inclusiveness. And I think what is going to happen is that we'll develop better and better tooling. It's like bug finding in code, right? If you look at real code, there are always more bugs, and you decide which bugs to fix, and you fix the most severe bugs first. And I think the same thing will happen with models, right? As we sort of look at models and get a deeper understanding of models, we'll understand both sort of small bugs of problems and as well as bigger structural bugs with models, and we'll find ways to fix it. So I think similarly, as software 1.0, right? I mean, we believe that we can write the perfect piece of code, but actually code is organic, it changes and it moves on and lives and it gets better over time and it changes over time. And I think the same thing will happen with models and our understanding of models. So one of the things I've been most impressed by is how the power of models changes over time. I mean, even the simple model as predicting of who I'm going to send an email to. At the beginning, nobody thought, oh, model is always going to be too slow. It's never going to work really well. And now it's all models. It's so much better. I mean, if you look at Visual Studio Code, which does code completion, which is really amazing technology, right? You could imagine that much more technology is coming there as well. So I think all of these pieces will have models, will make some mistakes, but I think we also have the right goal in mind, and we'll create more and more tooling to make sure that we all do the right thing in the models as well.
Sudarshan, one quick question, which is very important for ICDE, because everyone's talking about AI, artificial intelligence, but I believe the data is sort of the bread and butter. So could you please sort of elaborate very quickly on this, how important is data and how the data community can be really relevant with all this hype going on with AI?
Well, so there are two different questions, two different parts of it, and I know we're running a bit over. So data is really the lifeblood of in some sense even a competitive mode sometimes, right? Because the more training data you have, the better the models get. I mean, models advance significantly, but then people in NeurIPS, they put their code out there, and you can take the newest code and try to train it on your data. So data is often a competitive mode, even though now we have seen tools like GPT-2 and BERT and so on, that are these large pre-trained models that you can adapt to different domains, right? So if you're in a new domain, data clearly is the mode. Now, what does it mean for the database community? I think we as the database community who manage the data, who manage access to the data, who look at the data lifecycle overall, I think this is one of the most exciting research areas in general. I mean, I'm super excited about both the work that's happening in our community, the direction that our community is taking. And I think our community is also relatively broad, right? Our community is focusing on data, but that means, going all the way through the data lifecycle, but with data always at the center. And the other thing that I like about our community, very much what I'm so excited about, is that our community is building systems, right? So we don't only develop theoretical algorithms, but in the end, we actually go ahead, we implement these algorithms, we try them out in real systems. And that is actually the ultimate proof. In industry, what matters in the end is that you build something that the customer appreciates and likes. And without building anything, everything is just theory. So I think this combination of taking interesting or developing the foundation, taking this foundation and all the way up to a real system is, I think, a big strength of our community, which spreads, going all the way from ICDT and pods all the way to like segment VLDB and ICDE here.
Mm-hmm. Good. Thank you very much, Johannes. This is the point where everyone normally applauds, but this virtual conference, I don't think you can hear it. A few of us can.
Yes.
I'm sure there is a lot of applause virtually going on out there. That was a wonderful talk, Johannes. Thank you very much. Before we sign off, thank you. Before we sign off, we have the next session starting in about 20 minutes. So we will open up the rooms shortly, and then you can join the tutorials, the industry sessions, and the research sessions. I would also like to mention that there are three more keynotes, one today afternoon, one tomorrow morning, and one on Thursday morning. And there's also an award session on Thursday with 3 awards. One is an IEEE award. The second is a Rising Star Award. And the third is the 10-year Best Paper Award. So please do join. There are some really fantastic talks coming up in all the keynotes, as well as 2 wonderful talks coming up in the award session. Thanks. Those of you who want to view the tutorials can stay on in this room. Others can quit this room and then go back to the ICD schedule to join whichever session you're interested in. Thank you. Thanks again, Johannes. Goodbye.
Bye.
Thank you. Goodbye.
Thank you.
Hi, this is Rhonda. I have turned the host over to the student volunteer that's taking over in this room. So I'm leaving the meeting now and I'm going to open my room.
Thanks, Rhonda.
Thanks, everyone in the audience. Bye.
Hello.
Mohammed, we can hear you typing. Can you hear us as well?
Oh yeah, I can hear you.
Okay, excellent. Okay. So
Yeah,
when we
I'm typing checking on Ibrahim. طبعا اوكي مثلا
Ibrahim, good morning. Can you also speak so we can make sure that we can hear you properly?
Good morning. Can you hear me?
Yes, yes, fine. Thank you.
Great.
But for some reason, we see Mohammed Mogbel under your picture. That would be a bit confusing, but that's okay.
Yeah, I can start my video, I think, here.
Mohammed will not mind, of course, because in that way he's going to look younger.
Yeah.
Mohammed, can you also please share your screen so we can see that this can be done easily?
Yes, I can start sharing it now. Yes. Okay. I did share it now. Is it okay?
Yeah, perfect. Thank you, Mohammed.
Yeah.
Thank you, Manuel.
Mohammed, Ibrahim, how do you want to handle questions? I mean, can we take questions, let's say, at the end of each part? Is that reasonable?
I think feel free to have your own base of questions here. I mean, we can stop anytime and answer questions, make it more interactive, like real ones. So I would leave it to you. If you have an important question, you want to stop us anytime, we can do it.
Okay, thanks. So I'll monitor the feed, the question feed, and if I see something important, I'll stop you.
Yes, okay. Please. Yes.
Okay, so it's time to start again. Welcome everybody. My name is Manolis Koubarakis. I'm the session chair for this first tutorial of ICD 2020. The tutorial is on the topic of machine learning and big spatial data. And it is given by Ibrahim Sabek and Mohamed Mogbel. They are both experts in big spatial data and machine learning. Starting with Ibrahim. Ibrahim was a PhD student of Mohamed in the University of Minnesota until recently. He has done his PhD in exactly this area that the tutorial is about. And actually his dissertation won the University Dissertation Award from the University of Minnesota. And Ibrahim is now a postdoctoral fellow at MIT, working on similar topics like the ones that the tutorial is about. Mohamed is the chief research scientist of the Qatar Computer Research Institute and also a professor at the University of Minnesota. He's very well known for his work in spatial databases, especially on big spatial data. And he has received a lot of awards like best papers and things like that in this area. This session will be run exactly as the previous session, the keynote by Johannes. So feel free to ask questions by using the Q&A functionality. And I will pass them to Ibrahim and Mohamed. With this, I would like to pass to Mohamed for starting the tutorial. Mohamed will start, and then Ibrahim will continue. Thank you very much.
Okay,
Mohamed,
thank you.
over to you.
Thank you, Manolis, for the introduction. Thank you, everyone, for coming online. Looking forward to meet you in person in the near future. But for now, I think online is our best bet. And thank you, Bhavani, and everyone, the ICT organization committee. Doing this in a couple of weeks, I couldn't believe that they would be able to do it. So that's very good. Excellent. So the topic of our tutorial, machine learning meets big spatial data. I will walk with you for the first 20 minutes of the tutorials, 20 to 30 minutes, and then Ibrahim will go on next. My job is to make it more of a teaser for you or to convince you why we need to think about this topic and why there's a big gap in the machine learning and big spatial data, and show you opportunities there. Ibrahim is going to detail more into existing techniques and state of the arts and where can we go from there. Start by what is the rise of machine learning. It's not something that I need to convince you about. You have heard machine learning everywhere, and if you just look at the rise of machine learning in different fields, this is just some articles, not research articles, more of magazine style. You find it Forbes, rise of machine learning and AI in improving lives, the rise of machine learning in cybersecurity, rise of machine learning in astronomy, in different fields. So everyone now is like looking around for how to use or how to deploy, to exploit machine learning for their fields of interest. One of my favorite quotes by Google CEO, when he said, machine learning is a core transformative way by which we are thinking everything we are doing. Meanwhile, as someone working with big spatial data for long, it has become ubiquitous. All of us now are aware about mapping, routing. We use spatial data as some kinds just granted around us, and new technologies, startups working with it. And even if you go for a bigger scales and using your own location data and finding your route around, existing of satellite data, even medical data like X-rays is treated in a spatial way. Social network uses the spatial data. So it becomes around us in a way that becomes ubiquitous, and we don't feel really about it something new. Also just 10 years ago or 15 years ago, you wouldn't even care about much of this spatial data. The question now, can we use the machine learning for big spatial data? And if these two creatures got married together, what's going to happen here? So we have plotted this kind of diagram here. On the horizontal axis, we're thinking of machine learning fundamental algorithms, where there are non-spatial machine learning algorithms and there are spatial machine learning algorithms. And in the application side, again, on the vertical axis, I have non-spatial application and spatial applications. And in fact, most of the things we look around for using machine learning, I would classify it as belonging to the same quarter, which is you develop machine learning fundamental algorithms and you develop non-spatial application for them. And most of the algorithms, a large majority of them, think of spatial data as just one more data into your equation. Why should I differentiate between non-spatial data and spatial data? I'm just doing my algorithms, my techniques, my system that deals with data, and that's it. If you're going to talk to me about spatial data, yeah, just use my algorithm and it will work. My job in this tutorial is to convince you that this is not enough. Do not think of spatial data as the same as non-spatial data. Spatial data has its own characteristics and its own things that needs to be treated spatially and spatially. And I will show you different things here. In particular, I'm going to talk about these three other quarters. I'm going to motivate these three other quarters for you, and Ibrahim will detail more techniques. And three other quarter, what does it mean to have spatial machine learning fundamental algorithms to non-spatial applications, or the other two quarters here? And also, what does it mean to convert non-spatial machine learning algorithms and techniques to be spatial one? And does it worth it or not? Is this something we want to investigate, want to look at or not? So let me start as a motivation with this quarter here, which is basically spatial machine learning fundamental algorithms for non-spatial applications. One of the very common applications for machine learning is knowledge-based construction. And when you think about knowledge-based construction, most people think of it, okay, what is the spatial thing has to do about it? I know how to do my knowledge base for any kind of data. And this is what people are using mostly. So what is the process of knowledge-based construction? Basically, you have your box of knowledge-based construction system. Your input is a set of articles, PDF articles, websites, Wikipedia, whatever you can get as an input. And then a set of rules. And these rules apply to the document you are given, that apply to the input documents. And out of these rules and documents, the main role of a knowledge-based construction system is to extract relations and then produce a table of relation of what they consider facts. For example, you can make a spouses knowledge base. From these documents and these rules, you can say that person 1 and person 2 are married, like Barack and Michelle are married. That's, you are extracting a fact or you are constructing a knowledge from unstructured documents. Okay, and then came the field of probabilistic knowledge-based construction. So it's not a knowledge-based construction per se, but you add the probability to it. And this is by another module called factual scores inference. And the difference here is that when you report a knowledge base, when you report a knowledge, you report it with a probability of being correct. For example, here in the spouses knowledge base, we can report that Barack and Michelle are married with 0.85 probability, 85%. And Joe and Katie are married with 52%. Joe and Lily are married with 46%. Then the interpretation of this probability is left to the user, how to interpret this probability. But at least the knowledge-based construction here is not giving you things that as facts or not, it gives you more as a probability. This one, a lot of systems came out of probabilistic knowledge base. A lot of systems from industry and academia have worked into this with a lot of valuable input and systems that are widely used. In fact, maybe the most common one or the most recent one is a deep dive system that came from Stanford, and it has been really used in human trafficking and geology and different things. And in fact, you can even find CNN, Forbes articles about it. And Apple acquired dark data specialist lattice data for $200 million, which was based on deep dive. So deep dive in general is one of the most, or the state-of-the-art system for probabilistic knowledge-based construction. When we look at deep dive from inside, this is how it looks like. Deep dive, which is a machine learning-based knowledge-based construction, it's built on scalable implementation of what's known as Markov logic networks. I don't have to go to you in details here, but it has a language module, grounding module, inference module, and so on. If you look at the word spatial here anywhere, there's nothing. And the question is, why there's nothing? maybe it doesn't work, you know, I mean, or maybe everything here can work in spatial the same exact way like it works with non-spatial data. So we got deep dive, we installed it, we played with it, Ibrahim gained really good expertise about how to work with deep dive. And then we said, okay, we're gonna give it some problems that we know it has spatial factors. So we tried deep dive with spatial data with this real example. We have 4 cities in Minnesota: Minneapolis, St. Paul, Eagan, Rochester. And these 4 cities, we know the education level of each city, which is 0.7, 0.7, 0.7. They have the same education level. This is kind of real data. And we know that the city of Minneapolis has high crime rates. And then we want to use deep dive to know the crime level of the 3 other cities. So here are the rules, inference rules we give to deep dive. A predicate 1 says city X has high crime rate. Predicate 2 says cities X and Y have the same education level. And the rule is simple. If P1 and P2, which means if a city has a high crime rate, and if 2 cities have the same education level, then Y would have high crime rate, same like X. That's the simple rule. We apply deep dive here, we get this answer. Because we have the ground truth, this is not an accurate answer. This is a pretty inaccurate answer. We thought about it, why deep dive is not working here? And the simple answer is, okay, you know what? If you are in an interactive session, I will ask you to answer this question. But okay, let me go on. Here is crime data is a spatial thing. If 2 cities are neighbor, they are likely to have similar crime rate. If 2 cities are neighbor and have the same education level, they are more likely to have the same crime rate. So we said, okay, this is what we can do with deep dive. I will add a 3rd predicate. Cities X and Y are within 80 miles. So now I have 3 predicates. If predicate 1, predicate 2, and the predicate 3, all of them are valid, then Y would have high crime rate. What does this mean? This means if the city X has high crime rate, then X and Y have the same education level, and X and Y are within 80 miles, then Y would have high crime rate. And now we injected the spatial thing into the rules given to deep dive, which we run deep dive here, we get another difference than the one before. It's more accurate, it's actually more accurate, but it's not good too. It's not good either. This is not what we should get. We should get really better answers than this. We replicated this algorithm, this technique on a different data sets. We get Ebola infections later in Liberia when Ebola was a big thing at the time. So these are 4 counties in Liberia. And these 4 countries, we know the sanitation level at the 4 countries, 0.6 for each one. And then we know that the first county has high infection rate. We want to know the other 3. So we exactly did the same. Predicate 1, county X has high Ebola infection rate. Predicates 2, counties X and Y have the same sanitation level. And the rule, if P1 and P2, then Y would have high infection rate. We apply this to deep dive, we get an answer, which is not accurate. Our interpretation, deep dive does not understand spatial data, or sorry, we did not express spatial data in rules. So we did a 3rd rule here. Counties X and Y are within 150 miles. And the predicate is, if X has high infection rate, then X and Y have the same sanitation level and within 150 miles, then Y would have high infection rate. We did it again in deep dive, we get better answer, but not accurate. Usually I would ask a question here, why you think it's not accurate here? And let me come up with the answer. The answer that this thing is here are not accurate is that you are expressing, or we are expressing the spatial functionality in the rule, not in the engine. Yes, we did a spatial function here, or yes, we did spatial predicate, and yes, deep dive allowed us to put a spatial predicate, but this spatial predicate did not make it to the engine. And why this is bad here? Because when you say cities X and Y are within 80 miles, this is so rigid to spatial data. Because now you are saying, if a city is like 75 miles, then this predicate is true. If a city within 85 miles, then this predicate is false. But 75 and 85 are not far from each other. And actually 85 is like 80 here with respect to distance. So the reason is that deep dive deals with predicate as 1 or 0, which could be okay for non-spatial data, but this is not okay for spatial data. Again, Deep dive deals with predicate and give an answer either 1 or 0. It's okay for non-spatial data, but this is not acceptable for spatial data. Spatial data is a different treatment, because what you want to say, the farther the city is, the lower probability it would be, not to put a rigid thing, it's either 80 or not. So what we wish to have is this rule here, predicate 3, the one marked in green now, I scratched the red one and put a green one. This is what we want to do. We want to do predicate 3, the closer Y and X together, the higher Y crime rate. And again, the Ebola thing, the closer X and Y together, the higher Y infection rate. This is the predicate we want to have. And then one applies the rules, that's the 3 predicates. However, doing this deep dive would not work, because the answer to this rule is a spatial answer, which need to be, has this gradient, cannot be 0, 1. And deep dive cannot support this. So what we need here is to go inside deep dive and look at the machine learning modules and let it understand the value of spatial data, or the unique properties and unique characteristics of spatial data. Once we are able to do this, deep dive would work well with the rules with spatial data. So this is just an example here, just a motivating example for the need to support spatial data. Even if you think of a knowledge base, okay, knowledge base has nothing to do with spatial. No, it does. In fact, I'm not sure that there is anything now that has nothing to do with spatial. And I have another talk called Thinking Spatial, which is advocate for these things here. But to us here, this is a motivating example, is that if I can support the spatial data in the machine learning algorithm, deep dive or anything else, okay. So I made a teaser now for the first missing quarter here, which is spatial machine learning algorithm for non-spatial data. Okay, I will go now to another quarter, which is non-spatial machine learning algorithm, the traditional machine learning algorithm, how to use it for spatial data. Okay, and I'll give you an example of routing. What is routing? This is the most fundamental applications that we are almost using daily, right? I want to go from my home to the airport. I want to go from my home to work. I want to go visit my friend. I just put my GPS and let it tell me where should I go. So how many routing algorithms, how many routing calls you call every day? A lot of them. So routing is a big fundamental operation in any kind of spatial, in the spatial data. And in fact, the number of companies that are based on routing are huge. Started from ride-sharing companies to just mapping like Google Maps, Apple Maps, and different things here. And how routing work, basically, you have source and destination, and then you have the routing algorithm. Routing algorithm takes 3 input, source and destination, and takes a map, and provide you routing. And there are tons of techniques of how to do routing. In fact, there are techniques now, which is actually mostly used in commercial things, is that you pre-compute the routes for most things. And when someone asks about source and destination, we give you the pre-computed route. Okay, routing to me is a premier example of the disconnection between industry and academia. Most people in academia, and you still can see this in papers in VLV, Sigmund, IZE, SIG Spatial, and all first year conferences, you can steal papers working, inventing new routing algorithms. I would really call to stop this. I mean, there's no need for doing better routing algorithms. Well, everyone is not looking at the routing. All industry actually is looking at the map. Why? Because you know what? If you have the best routing algorithm ever, but you have a wrong map, your routing algorithm would give me garbage, even if it's the most efficient routing algorithm ever. And if your routing algorithm is not the most efficient one, but acceptable in performance, and your map is accurate, your map is good, you will give me much better route. And guess what? I mean, all the battle now between industry is on the map, not on the routing algorithm. It's all about the accuracy of the map. And this, you don't take it for granted that the map is accurate. This is not true. In fact, the map is about 2 things. If you take the map, think of it as 2 things, topology and metadata. What is topology? Topology means the road segments of your map, okay? And you can argue, okay, your city has the best coverage all over the world. That's fine. Other cities are not. But even if your topology is accurate, what is more important is the metadata of the map, which is very hard to say it's accurate. What is the metadata of the map? Metadata of the map, for example, what is the weight of this road segment? If you have a road segment on a highway in a rural area next to your home, to the map, to the routing algorithm, it's a road segment plus a weight. A weight means the distance, the time takes to pass this road segment. And by the way, this cannot be a single number. As simple as this. If you put a simple number as a weight of the edge of the road network, that's wrong. Because this number changes from day and night. Changes from weekends to weekdays. So you really sometimes, I mean, some of our experiments, we did like 168 numbers per edge. So figuring out the map, the topology, or the metadata, machine learning can play a major role here. I'm sorry. Ibrahim will go with you in details on different techniques that use machine learning to come up with the map. Once you get the map right, now you can go ahead and apply your favorite routing algorithm. I'm not going to tell you which routing algorithm you will apply because the map is accurate now. And for example, I give you, there are many articles that say, for example, Google Maps leads about 100 drivers into a muddy mess in Colorado. Another article, Google and Apple Maps have plenty of errors. It's all about maps. But then I have this table, this huge table that compares Google Maps versus Apple Maps versus Waze versus MapQuest. These are 4 common applications that people are using for routing. And I think there's more than 40 factors comparing Google Maps, Apple Maps, Waze, and MapQuest. None of these 40 factors talk about routing. They talk about the quality of the map, the accuracy of the map, more the interface, different things, but not about the routing, because it's done. That's why I still feel bad when I see papers coming field segment, ICD segment, especially talk about routing algorithms anymore. So anyway, machine learning can really help us here in coming up with better maps. And we'll show you a detailed example. Ibrahim will go with you in detailed examples here. Okay, so now I want to give you a teaser about the third quarter here that was not covered before, which is having a spatial machine learning fundamental algorithms for spatial applications. So we have 2 spatial things here. And I'll give you an example of a spatial regression, or what's called autoregression here. A spatial autologistic, it's called autologistic regression, which is basically a spatial autologistic regression. It's find whether a spatial phenomena exists or not based on neighbors, values, and features. It has tons of application. This is a classical problem, decades old problem. It has been there for 20, 30 years or something, which is basically weather prediction, birds migration, different application. And the whole idea looks like this. If you look at the grid here, each grid has a value 0 or 1. 0 means this phenomenon exists. 0 means that this phenomenon does not exist. 1 means that this phenomenon exists. And this phenomenon could be, there's rain here at the cells with 1, no rain at cells with 0, and so on. And then each cell has what's called features. Like you see, a first cell here has X1 and X2. So each cell here has 2 features. These features could be the humidity level, could be the shade, the vegetation of the thing. So each cell has a value, either 0, 1, and the future, whether this future exists or not. And if you see at this grid here, there's a cell I14 has a question mark, which means it's missing. And what autologistic regression do is basically predict or find out what is the missing values here. Okay. One thing you can say, okay, missing value, I'm going to interpolate. No, that's not what the statistician do. And I'm not here to argue what is the best way to fill in this value, because there is already an equation for this. And I did not come up with this equation. You see this logarithmic equation. I did not come up with this equation. This equation has been there for decades. Spatial statistician came up with this equation. And basically this equation, try to find the missing value, and Z here is the missing value we're looking for. The probability of this value equal 1, equal so and so. What I want to show you here is that this equation really rely on 2 regression parameters, beta and eta. Actually not 2, many parameters here, because eta is 1 parameter, but pj, that could be, in our example here, there are p1 and p2 because we have 2 features. If we have more features, it could be more and more. Okay, the job of all spatial statistician is to use the values that is completed here to feed in this model and come up with the values of the regression parameters. Then when they have the value of regression parameter, now they can apply it and find the missing value. Okay. This solution has been there for long. However, learning regression parameter for like something like 80K cells, which is not big, that could take more than 1 day. It's very expensive to do this equation. It's very expensive to solve this equation. And as a result, people who are doing spatial statistics start to use this equation, but not to use fine-grained cell. So let's take for every 8 cells, make them as 1 cell, and so on. So they simplify the problem a lot to find solutions, and then it's not going to be accurate. What I want to show here is that this is an open problem for machine learning people, because you can use machine learning to solve this equation in a very, very scalable way. And Ibrahim will go with you in details about this. So I'm done with my part here. My job was to motivate you and to some kind of an eye-opening to show you that using spatial data and machine learning can open things that we did not think about it as solvable before. I will stop sharing here, and Ibrahim will share his screen and continue from here. I'm still alive, so I'm still online, so I can answer questions with Ibrahim anytime.
Okay, so I'm gonna share my screen here. So can anyone hear me?
Yes, sir.
Okay, great. So hi, everyone. My name is Ibrahim Saber. I'm going to continue with you the rest of our tutorial today. Basically, I'll go through the details of the different techniques in each quarter that we have in our landscape. Give the main idea, describe some detailed examples and applications. And after that, I'll give an overview of the end-to-end systems that support spatial data and machine learning together. So let's start with the first quarter that we have here, which is spatial algorithms for non-spatial applications. And the main theme here in this quarter that, as Professor Mokber mentioned, that we have non-spatial applications, and we want to make sure that the existing machine learning algorithms used inside these applications have support for spatial awareness so that we can have a better performance at the end. And we are gonna start with the first example that we have here, which is knowledge base. And as a quick recap for the knowledge base example that Professor Mokber has shown before, we use Deep Dive, which is one of the most popular knowledge base construction systems to build knowledge bases from spatial data. And we still found that we have some limitations in inferring very accurate factual scores. Actually, they were not that accurate given the spatial properties that we have in our data. And this is because Deep Dive, for example, doesn't have a support for the predicate B3, as Professor Mokber mentioned before, which is like the closer Y and X is a higher Y crime rate, because this kind of predicate support the gradual semantics needed for the spatial applications. And Deep Dive doesn't have this spatial support. So to resolve this issue, one of our work recently on the knowledge-based construction systems called SAIR, we proposed in this system to add the spatial awareness inside the different components of the knowledge-based construction system. And basically, we started to work with the internals of Deep Dive, which is built on top of a popular framework for machine learning called Markov Logic Network. I'll give details about Markov Logic Network later in this talk. And we started to have a spatial variation of this Markov Logic networks. And using this variation, we built a very powerful spatial aware knowledge-based construction system. And as you can see here, this is like the high level architecture of our SAIR system. We added the spatial extensions in the different components like language, grounding, inference. You can see here we have spatial data types and functionalities to allow the people to express the semantics of their spatial problems. And also in the grounding phase, we added some spatial SQL query supporting for constructing the knowledge-based relations from spatial data. And also in the machine learning core itself, used inside the knowledge-based construction system, which is about the inference, we added a spatial aware inference algorithm called conflict-based sampling. And it was very powerful for inferring the factual scores of the spatial relations that we have in the knowledge base. And by doing this, we got more accurate performance numbers in the factual scores using, say, a comparator deep dive. Going back to the same examples that we had in the motivation, you can see here in the green scores that we had much better confidence scores compared to the one that we have in deep dive. And if you are interested in more details about SEA itself, you are welcome to attend our presentation on Thursday, research session 21. We have a paper there, and we are gonna give more details in our presentation. So now we are gonna move to another application here in this quarter, which is about image analysis. And basically, we are looking for the problem of object detection in images. So basically, you have an image, and you have some objects in this image that you want to detect. For example, you have a handwriting letter like O here in this input image, and then you want to detect it. And traditionally, this problem has been solved with traditional deep learning approaches like convolutional neural network. And actually, they are performing very well, this kind of approaches. Well, they are dealing with dense cases, like images with dense objects and this stuff. However, it's surprisingly not performing so well for the sparse cases. And specifically, if you are running on a low resource device like mobile devices, because it's very computationally expensive. And the idea here that some people come with a very efficient idea. So instead of like using traditional convolutional neural network, we can borrow some spatial partitioning techniques like quad tree to remove any unnecessary computation during the process of computation of the convolutional neural network. And by doing this, they are making sure that all the different layers of the convolutional neural network pipeline, including the convolution itself, rectification, Boolean and upsampling, and so on, all of them are compatible with the quad tree. And for example, here, if you can see, this is like kind of image. And while you are going through the high resolution layer of the neural network that we have here, we can focus only our computation on the gray parts that are coming from the quad tree partitioning. And now we are ignoring anything here in the white space. So this will save both like storage and time costs and make it very efficient. So this is like another example of how we can take a very popular algorithm like convolutional neural network and make it very spatial aware and using technique like quad tree, and then we become very efficient in the processing and in the storage cost. Another example here we're gonna show also in this category is event detection. And in this application, we detect events based on a sequence of social signals. Basically, we can use tweet counts that we can observe within a certain time period and within a certain region to give us a sense if there is any abnormal event is happening or not. And traditionally, this problem also can be solved using neural network. And one of the successful approaches has been used extensively to do this is long short-term memory recurrent neural networks. However, this kind of approach, if it's used by itself only, it's focusing only on the temporal aspect more than the spatial awareness. And it generates kind of bias in the results. And to resolve this bias, we combine something like spatial convolution with this LSTM networks. So now we embed here convolution filters with some spatial information during the process of like our constructing neural network here. And by doing this, we come up with more accurate results at the end. And this approach called convolutional LSTM, and it started to be very popular in the spatial domain since 2018. So this is also another kind of application to embed the spatial awareness inside the construction of the neural network itself and how to process the different layers of the neural network. Last example here in this category that we have here is recommendation system. And basically, a recommendation system is an engine that analyzes the user behavior to recommend interesting things and interesting items. So basically, in the recommendation, the recommender system starts to gather some information about the user item ratings and build a recommendation model out of these ratings, and then use this model to answer any user query about recommendation and give us some inputs, some outputs here. And one popular approach is to build a collaborative filtering algorithm based on factorized matrices. And although this algorithm is very popular and have some like success stories in different commercial products, the problem here that also it's still missing the spatial dimension that can be important also for the recommendation quality. For example, people in the same area could be interested in the same thing. We can think of this like if people in the US could be interested in watching some kind of movies, like they are really interested in action movies, for example. But if we think of this like in the Middle East area, could be like people interested in another kind of movies. So having the spatial dimension in the recommendation quality itself could be very beneficial. And to solve this, people started to add the spatial and temporal correlations across the user and items used in building the collaborative filtering approach. And one of the things here I'm sharing, one of the very popular work in 2009, they added some spatial regularization terms for the user and items while building the model itself. And by doing this, they have achieved more successful recommendation results. So in conclusion here, we just covered few examples of adding the spatial awareness inside the machine learning algorithm used for the non-spatial applications. And of course, these applications or like these examples that we just talked about are not all the examples. In fact, we are encouraging people to start like moving some applications from this quarter, the non-spatial applications for or non-spatial algorithms for non-spatial applications, to move kind of these applications to the quarters that we just talked about by adding some spatial awareness inside the algorithms used. For example, in digital health and cybersecurity, people can start like thinking spatially on how to add the spatial dimension to optimize performance, as we did in knowledge base and image analysis applications. So now we're gonna move to the second quarter that we have here in our landscape, which is specifically for non-spatial machine learning algorithm for spatial applications. And the main theme here in this quarter that we wanna make sure that we use existing non-spatial machine learning techniques. And in this case, we are using the machine learning techniques here as is, as a black box, without any spatial addition inside them, to efficiently solve long-lasting spatial problems. And Professor Mokbel talked about one of these applications, which is routing. We're gonna give more details about the routing application and also give details about other applications like traffic prediction, outdoors localization, spatial object detection, and forecasting. All of this kind of spatial applications, core spatial applications we need in the spatial domain, and all of them are making use of the non-spatial machine learning algorithms as is. So we found also in the most of the recent work in this quarter focus only on deep learning approaches with few other state-of-the-art classical approaches like classification and cluster. So we gave like some examples on the different applications as we move on. So we start here with the routing application. And a quick recap also, as Professor Mokbel mentioned, it's not only about routing algorithm itself, it's also requiring having the correct maps. And also this includes having the correct topology and correct metadata. And also we are gonna give some recent advances in both of this, like metadata and topology making for having correct maps. So we start here with the topology making itself. So for topology making here, we are gonna cover a couple of works here. And basically the first work is route tracer system. And basically in this system, they are trying to construct route maps from satellite images. And they are using some machine learning techniques to do this. So basically in this problem, classical machine learning approaches are called, in this case, segmentation approaches. They try to classify the pixels in each image, whether it's belonging to a route or not. We found that, and also like the people in this like routing area found that this could have some high error rate if we have like some messy satellite images. And in this approach, which is using neural network here instead of like having classical approaches like classification or regression, they started to have much better performance by using iterative search process guided by convolutional neural network So they start to incrementally build the route, or like the route segments that we have, point by point. And this implementation process is guided by convolution neural networks. So they search point by point using convolution neural network. And as you can see here from this example that we have, this is a final output coming from the segmentation methods and the route tracer method. That you can see here that route tracer can have much better performance in detecting some challenging routes like bridges, like turns, and this kind of stuff. And this proved the efficiency of using convolution network, even if it's not spatial aware, using it as is in some kind of applications like topology making. Another kind of work also for the topology making coming from Facebook AI, and they are providing something very cool called Map with AI. They are also using the convolution neural network, but in a different way. They are using it to extract very improved features from high resolution images. And this feature will be used to build very accurate classification approaches, like have very weakly supervised learning classifiers, but now based on very improved features. And as you can see here, this is like the output on the right-hand side here, the output from the Map with AI. And it's very, very accurate when we compare it with this output coming from the segmentation methods also. And even people now started to combine this kind of approaches with OpenStreetMaps and to get more and more accurate results. So the main message here in this approach is that also using the convolution neural network can improve the feature extraction, also used for classification or regression in the spatial domain. So now we are moving to the metadata part. So we just covered two works for the topology making, now for the metadata part. And in this problem, we assume that we have the root network, like we have here the segments, but now we don't have the weights, and we want to predict them. And traditionally, these weights are estimated as one number, but as Professor Mokbel mentioned, it should be accurate if you are estimating this based on time granularity, different time granularity, because it could be different from rush hours than like night hours. So you need to have specific time granularity when you are estimating these weights. And in this work, instead of like having fixed value for each weight, we are they are like in this approach here using some ridge regression analysis to predict this time granularity based weights. So basically here they have the input as a set of trips. Each one of this trip could have like the pickup time location, drop off time location, and the pass. And after that, they are constructing a set of linear equations out of these trips, as you can see here. For example, this from trip from B to H. And then we have like a linear equation based on the weights that we have here in this trip. And after doing this for all the trips that we have, we end up with having X equations in Y unknown variables here. And the problem here is transformed to solving these equations within like this unknown variables. So the first step is starting to use the dimension reduction methods to reduce the number of equations and reduce the number of unknown variables. And then we pass this equation and unknown variables to a very classical approach for regression analysis called ridge regression analysis. And by doing this, we can have the edge weights per granularity. This is like an example from the Qatar trips case study there. And we have here, for example, 10K equations in 500K unknown variables. After the dimension reduction, we can improve this by having only 1K equations in 5K unknown variables. And then for our granularity, we can have edge weights per hour. So here we are using a classical ridge regression analysis, not like deep learning, for also detecting the metadata weights that we have. Another kind of work also focus on detecting this weights, also coming from ICD 2019, and it's focusing on sophisticated weights. More than having like one weight per each time granularity, we can also infer a distribution, like a speed distribution for each certain time granularity. For example, here we can have this like root segments, and the edge weight here is instead of like having a weight like W as we had in the previous slide, we can have a distribution here. So for example, here at a certain time granularity, we can say that the probability of having speed like traffic speed between 5 and 10 is 0.3, and those from 10 to 15, for example, here is 0.5, and so on. And of course, this kind of detailed information is not available for all route segments. So the problem here that given this few known like speed distributions, can we infer or predict the missing ones? Like, for example, here in our example, we have the speed distributions for E5 and E6. Can we use them to infer the speed distributions for E1, E2, E3, E4? And the output should be something like this. So the solution here starts by putting this kind of speed distributions that we have and the adjacency matrix that we have between the graphs into a suitable format for the neural network solution. And then we apply graph convolution operation on this like input data that we have. And basically here in the graph convolution operation, it's similar to the convolution neural network, but now instead of having like the traditional filter, we have this filter based on each network node and its neighbor in the graph. So based on the neighborhood in the graph. And after that, we can apply the traditional neural network pipeline and get the completed weights event. So the main message here also that even we can use the machine learning to infer more sophisticated weights, not like only one number per each time granularity, but also we can use this with a speed distribution or like inferring distribution at different time granularity. So now we're done with the metadata and topology making. Just for completeness, we are gonna give also one recent advanced machine learning based routing algorithm. And it's also coming from ICD 2018. And the interesting part about this routing algorithm is that it introduced a new concept for routing, which is like learning how to route. So basically, you can define the features that you are using for having a good route. For example, here, you can say that other than the distance functions that we can usually use for like having best routing algorithm, we can use, for example, route condition, like whether the route that we have or this segment is ready or not, if there any work construction in this part or not. And by defining these features, you can have an opportunity to learn more personalized routes for each user. And the solution here that given a complete route network, now we have the route segments and we have the weights for these route segments and some trajectories as inputs here coming from the trips, for example. First, they are starting to cluster this route network into something called region graph. So now we are trying to group some nodes in the route network and like try to construct a region out of these nodes. And after that, we learn some preferences for the trajectories in each region. And if we have some trajectories that are missing some preferences, we can also transfer the preferences from one trajectory to another if they have a high similarity. And this similarity can be user defined. After that, we have a complete set of trajectories with learned preferences. And whenever we have a user query based on the source and destination, we can recommend, based on the learned preferences for these trajectories, we can recommend a suitable route. So here we are using classical approaches like clustering, learning approaches like regression or classification. Even with this simple and the classical approaches, we can also achieve very sophisticated routing approaches. So we're done now with the routing applications. We are gonna go through another application, which is traffic monitoring and prediction. And traffic monitoring and prediction is a very classical problem in the spatial domain. However, existing solutions before this like big era of the deep learning approaches were focusing only on the short-term prediction, like prediction for 20 minutes only or maybe less than this. But now with this recent advances in the machine learning, people now started to question the long-term prediction, like can we like predict for days, for months, something like this. And we're gonna give some examples here for how we use deep learning for, or like in general, like advanced machine learning approaches to do this prediction. Specifically, we have 4 examples. So let's start here with the first one, which is using the residual networks. Specifically, they are using here a combination between the convolution and the residual networks. Like this is a variation to handle both spatial and temporal dependencies. And in this approach, they are just getting the traffic input maps and divide them into different time spans. And in parallel, they are applying this pipeline of the convolutional residual networks on each one of these traffic maps. And then the results of the prediction are fused together to get the traffic prediction. And in this approach, we can find here that also having this convolution based on spatial filters can improve the performance of the spatial results that we have for the traffic, because at certain parts, if you have a traffic with a high rate, you can have also like, you can infer that, or you can make sense that also the areas around this part or this region could have also high traffic rates. And without having a specific convolutions that can capture, convolution filters that can capture this spatial semantic, you cannot have accurate traffic prediction. A second approach here is using also a variation of the convolutional recurrent neural network, which is called diffusion convolutional recurrent networks. And the main idea here is to consider the pairwise spatial correlations between the traffic nodes. Like, for example, if we have traffic sensors deployed and we are getting information from each other, so how can we capture the spatial correlation between these traffic nodes? And in this approach, they are modeling the problem as a graph problem, where we have the traffic sensor node as the nodes in the graph, and the edge weights between these different nodes capture the spatial correlation. Now we need to do a convolution over this like graph that we have, but now while considering the inflow and outflow traffic that we have. And to do this, most appropriate approach is to do the diffusion convolution recurrent neural network. For example, here, we can start from a node here at iteration theta 0, for example, and we do convolution based on this node and its neighbors in the graph. And in the next iteration, we start going from the neighbors that we already convoluted was in the first iteration, and we do this over and over in the different iteration until we cover the whole nodes that we have in the graph. And after that, we combine like the all results that we got and get the prediction at the end. So basically here also, this is like another example for convolution recurrent neural network used for traffic prediction. Another work also using something called lookup convolutional recurrent neural networks. And also now, instead of using the spatial correlation between the traffic sensor node, we try to adapt an algorithm that captures the root network itself, the whole root network, like the whole root segments, and how to incorporate this inside the convolutional process in the traffic prediction itself. And the main idea here that for this like root networks that we have at certain time granularity, we generate a feature vector, and then for different time granularities, we have different feature vectors that we are gonna use inside the convolutional process. And after that, we got the prediction here was like an overview of the root networks that we have. So this approach is very efficient in capturing the spatial correlation also among the different nodes and the different root segments at the end. So the fourth approach here, and this is the last one for the traffic prediction, is using reinforcement learning. And basically in this problem, they are trying to focus on controlling the traffic lights and how to do this. Because it's a very important component in the traffic prediction. And doing this using a standard deep Q network, this was like recent work from 2018. They started to use the Q network to build an agent policy from the traffic training data that we have. And after this model is built, we can use it with any traffic input in the future. And then given this traffic input data that we have, we generate some action, agent actions, that say that how we control the traffic lights. And to get some feedback after a certain time period, we can collect all the the traffic lights control signals that we got and see if they are matching the actual results that we have, or improving the condition of the traffic prediction at the end. If not, we are going to signal it back to the DPU network to relearn the agent policy again based on new set of traffic input data. So this is another example of using reinforcement learning for traffic prediction. Now we're moving to another kind of application here, which is outdoors localization. So basically here in this application, we want to localize the people using their phones and without any GPS signal. And main idea here that we can get a fingerprint using the received signal strength from the cell towers and without using the GPS itself. So the approach here is having two phases. The first phase is the offline phase, which is training. We collect some lat long information associated with the cell towers that we get and the received signal strength. And once we get these fingerprints, we can build a localization model. And building this model could be using any advanced neural network application, or also using any standard or typical classification model. After we do this localization model building, we can, in the online phase, get also the RSS values only without having any lat long. And then we detect this lat long, the estimated locations that we have based on the localization model. Another application here, also very famous in the spatial domain, is quality forecasting. And specifically, one of the applications is air quality forecasting. So at a certain location, within a certain time period, we want to predict the quality. And usually we can do this using hybrid regression models to separately deal with the spatial and temporal correlation. However, more sophisticated approaches are recently proposed, specifically from Spatial 2018, based on convolutional neural network to capture these spatial and temporal aspects jointly. And this leads to more accurate results. And also they are following the usage of another variation of diffusion convolutional recurrent neural network, similar to what we have in the traffic prediction. Like the last example that we have here in this category is detecting the spatial objects inside images. And by detecting this geospatial objects, we mean that, for example, if you have an input image like this, and we want to detect the buildings from images, for example, or detecting cars or whatever, something like this from the images. It's very challenging because sometimes these objects are not aligned to the X and Y axis. And existing techniques could be confused if you don't have this. Sometimes it can have wrong answer, or sometimes it can give you a very approximate answer based on the minimum bounding rectangle. But now, thanks to the recent advances in the machine learning approaches and convolutional neural network, specifically the YOLO convolution approaches, we can get more accurate results and specifically get the actual shape of the object. As we can see here in the output here, the detected object, we can get the actual shape of the object, not like the minimum bounding rectangle, using something like multi-layer YOLO convolution. And the details, of course, are omitted here because we don't have time, space for this. So by concluding this applications that we already talked about in the second quarter that we have here, we have shown that also non-spatial machine learning algorithms, mostly here in deep learning approaches, can be used as is to solve this spatial application. And also it makes sense because machine learning algorithms could be also useful if we don't have the spatial variations. Now we are going to cover the third quarter that we have here, which is basically about having specifically spatial machine learning algorithm designed for spatial data analysis applications or spatial applications in general. And Professor Mokben mentioned one of them, which is a spatial regression. We're going to cover also other topics like spatial classification, spatial Bayesian, spatial sampling. Of course, there is a wide range of applications and algorithms in this quarter, but we are going to focus on the recent advances here just to give you the the taste of what's happening in this quarter only. So we're going to start here with the spatial autologistic regression. And as a recap, we have the issue here for this spatial autologistic regression for the scalability. The regression parameters, in case of having large scale data, can take so much time to be like accurately inferred. And this is a problem well known in the spatial domain. And what we did here is that we invented a new solution, which is very, very scalable based on the Markov logic network, similar to what we already discussed in the deep dive solution in the system says that we have already implemented. And basically, we are using a spatial variation of this Markov logic network. So now we have a specifically designed Markov logic network for spatial applications and used it for some spatial problems like spatial regression here. And we're going to see the details now. So basically, before we start about talking how we solve the spatial regression, what's Markov logic network in general, just for the people who doesn't know about it. So if you know, like this, there's a common problem in current machine learning approaches, which is machine learning is not that user-friendly for different people. So not so many people can use it. Specifically for deep learning, it needs experts and highly trained scientists to implement it, write lots of code and do some hyperparameter tuning. So it's very sensitive and not so many people can do it. And Markov logic network is specifically designed to alleviate these problems. For example, here, it can be used to express the problems that we have in a very few number of logical rules. And this solution of the Markov logic network is covering a wide range of the statistical learning and inference approaches. And basically, this Markov logic network is coming from University of Washington, introduced by Pedro Dominguez there. And since then, it started to be used inside different kind of applications, and it proved its powerful nature to solve the problems. And recently, it's scaled up by Cressy from Stanford and implemented inside some applications like deep dive, as we have shown before. So what we have done here is that we built a spatial variation of this Markov logic network, because Markov logic network itself is not very equipped for the spatial data. The example that we had in the knowledge base like showed this like limitation. And what we did here that we added this spatial extensions to the stack of the spatial to the stack of the Markov logic network, as we discussed before. And by doing this, now we are ready to solve different kind of spatial applications or analysis algorithms, like spatial regression, and spatial classification, and spatial Bayesian network. Now we are going to focus only on the spatial regression, because this is like kind of application we are talking about. So how to use it, how to use this like spatial Markov logic network to solve the spatial regression problem. So basically, we are getting the regression equations, the autologistic regression equation, and pass it to a transformation module that transform this equation into a set of rules that can be used with the spatial Markov logic network. And these rules should have some weights, and these weights should correspond to the regression parameters that we wanna predict. And by passing it to the engine and solving the problem and solving the prediction for these weights, we are solving the problem for the regression parameters. As a specifically, this is like one example here, specific example. We have here an autologistic regression model for a grid of 4x4 cells. We only have one prediction variable and one predictor variable, which is x1 here. And we have here, for each cell, we have the neighbors coming from the vertical and horizontal cells. So basically here, Z4 having its prediction based on the different neighbors here we have, which is Z2, Z7, Z10, and Z3. So we just pass this equation to the transformation module, and we come up with a set of logical rules here that connect between the prediction variable that we have Z and the predictor variable, which is X, as you can see here, Z and X, connected by some bitwise and operators. And most importantly here, these weights of the prediction and predictors are also embedded here in these rules, which is like beta 1 and eta, corresponding to this weights in the regression problem. And after we do this transformation, we pass it to the spatial Markov logic network engine, and then we learn the parameters of beta and eta. And while we are doing this, we are solving the scalability issue, because Markov logic network is much, much scalable, more scalable than the existing and traditional approaches in the regression. So we move now to another spatial analysis problem, which is Bayesian modeling. And this problem here, it's very common, and it's used for analyzing the spatial data in general and estimating its parameters. And the module that we have here for the Bayesian is similar to the traditional regression equations that we have, but now we have Gaussian process assumption for the error term that we have here. And most probably here, the problem coming also from the estimation of the parameters, like what we had in the spatial autologistic regression. We cannot infer the correct parameter values in a very efficient way for large scale data. And specifically, if we are gonna go through the inference process, the distribution now will include more parameters to be inferred. And now we have, instead of having 2 parameters that we wanna estimate, we can have more parameters to be estimated, like more additional 3 parameters. And to solve this problem here in Bayesian modeling, one of the recent approaches is quadtree-based Bayesian modeling. And they are proposing that instead of having one likelihood estimation for all the parameters that we have, we can exploit a decomposition approach where we can estimate these parameters on different partitions. And then we try to combine this estimated parameters. And of course, this could be like an approximate approach, but it's started to prove its efficiency if we have larger scale data. So now we can see here that we have these different parameters during the inference of the posterior, like what we have here in the last slide. Here, the Bayesian inference, we have here C and M capital. So these parameters could be inferred here from the different partitions separately, and then we can approximate these parameters together at the end. And this approach is called meta-cracking, and started to be popular since 2018. Now we move to another application here, which is a spatial classification. It's very similar to the traditional classification problem that we usually aware of, but now we are doing this within a spatial context. So for example, here we have, similar to the traditional classification, we have training images which are labeled with predefined spatial classes as input. And the input here is that we have another image that we don't know the labels, and we want to predict the labels here. For example, here we have some pixels forming a spatial class, like what we have here in the brown, and also another class which is like the green here. So we need to have this spatial coherence between the different pixels. And this problem also started to be non-efficient in terms of getting accurate, in terms of getting fast response of the classification result when we have larger scale data. And this started to be solved by trying to abstract the way that we classify the spatial data. And now we do this by doing an approach called super pixel classification. So now instead of doing pixel by pixel classification, as traditionally is done in this kind of spatial applications, we start to group the objects in a form like superpixel, and this superpixel is still conserving the main properties of the spatial object itself. And after that, we pass it to the feature generation module along with the training image to get more accurate graph building for the superpixel classification model. And then we build a classifier that can generate the labels at the end. And when we have an input image, we can get spatial classes at the end in a very efficient way. So now here, the main message in this approach is that we can use some kind of abstraction like superpixel classification to improve the performance of the classification itself. Another approach is ensemble learning spatial classification. And it's very similar to the general ensemble learning. Basically, you are dividing the problem into different subproblems, and then we build a learner for each of these problems, and then we ensemble the output at the end for both of them. For example, here we can have like one image, and this image has two different zones. And for each zone, we can build a certain classifier, for example, a decision tree or something like this. And then we combine the results here in a more sophisticated way to preserve the spatial properties, to have like one final output at the end that represents the classification input that we need. So this is like also another borrowing idea from the ensemble learning, spatial classification. So the last application here in this category, or like the last problem that we are tackling here, is the spatial sampling. And it's very common if you have like large spatial data, you cannot like afford working with the whole data points that you have. So you need to select some representative samples from the two-dimensional, for example, if we have like working with maps or like any spatial domain, we need to have some representative samples from this domain. And we have a bunch of algorithms here like random, stratified random, systematic, and also systematic aligned approaches. All of these approaches are good, but now they show some bias if we have large scale data. And we had to use some machine learning approaches to get more accurate spatial samples in these cases. And one of the approaches here is to do this sampling in an incremental way, not like doing it like a whole iteration, but we can do this on different iterations. And we start by getting some sample, and then we get some feedback from the user, and then we store this sample once it's approved within a certain data structure that's very efficient for changes and updates for the different samples. And by doing this, we stop after the different iterations you specify as a user, or after you reach to a certain acceptable ratio for the accuracy. Another approach here, which is like the last one that we are gonna talk about, the spatial sampling here, using deep learning also to learn the spatial samples. And basically it builds a deep network. And this deep network can be used to preserve the original shape. So to sample some data points while preserving the spatial shape. Like for example, in 2D objects inside images, we can have more representative samples. And in the testing phase, these generated samples could be matched with the input to estimate the error for feedback. So basically it is used for kind of spatial applications combined with the computer vision application. So by like concluding this example in the third quarter, we now completed the overviews that we have on the landscape of the machine learning intersection with the spatial data. We have 3 quarters, as we mentioned, and we have shown here that machine learning can be beneficial for spatial data, and spatial data can be beneficial for machine learning. And we can pull techniques from different like worlds to improve the other world. And we encourage people to start like moving applications from the third quarter to the different 3 quarters that we have here, and optimize the performance to have better output at the end. Now I'm moving to the last part here quickly, which is like giving an overview of the end-to-end systems for machine learning and spatial data at the same time. For example, here the first stack that people started to use extensively in the recent days is a Spark-based spatial machine learning systems. As we all know, that Spark now is very booming, and it has successful stories for the spatial data management also. We have so many systems like GeoSpark, SimPad, GeoMesa, and people started to integrate this within the machine learning pipeline So basically, they are expressing the spatial machine learning operation using Scala language, and then generate some plans that can be using some operations from the Spark machine learning library. And then after that, if we need anything related to the data management or spatial data management, we can use any spatial Spark core layer, one of these systems, to make this computation during the machine learning processing is very efficient. And another system here also very common is Spatial. It's an open source based on Python, and people started also to have some increased interest in this now because now people started to work with Python very commonly. And specifically, this tool is very designed for the spatial data analysis algorithm like clustering, hotspot detection, outliers detection, regression analysis. And it's not very equipped for the deep learning approaches. So if we have a deep learning approach that we want to implement with a spatial data, Spatial is not the very first option to do this. Also, another system we have developed ourselves based on the spatial Markov logic network that we have shown before, specifically designed for probabilistic graphical models. And we can use it to build any kind of this graphical model like a spatial Markov random field, spatial hidden Markov models, spatial Bayesian networks, and also still not equipped for the deep learning approaches because Markov logic network itself is not equipped for expressing the deep learning approaches, but can solve equivalent problems. Another system here is JUDA, which is specifically for exploratory spatial data analysis. It's a very visualized system, and it has a nice visualization nature if people want to do some interactive data analysis for the spatial data. And recently, it has some cloud-based computation versions that can support very large scale data. Before that, it was limited for the desktop application, but now started to be supporting larger scale data. And of course, Esri also is a big giant in the spatial domain, and they are providing two different tools recently. One for deep learning called GeoAI, and can be used for deep learning, classification, clustering, regression, anything for these operations with the spatial data. And another tool called GeoAnalytics, which is for the traditional data analysis operations over spatial data. And they have also recent version, which is supporting the distributed computation for scalability. The last system that we highlight here is IBM Bears. And its main edge that it's one of the key players in the cloud-based service for the geospatial analytics, specifically designed for big spatial data, and can handle like complex queries at real time. So it has also successful stories for weather prediction and started to be used commonly among different people. So by doing this, we just conclude our observation about the synergy between the machine learning and big spatial data. We see that a lot of opportunities coming from the intersection here between the machine learning and big spatial data. And still we have some issues that we need to resolve or think of to protect this synergy, like privacy issues, ethics policies, and any kind of other problems that can come up with from the intersection of these two worlds. And by highlighting this, I'm concluding my talk, and thank you everyone for your attention, and we're happy to have your questions. Thank you.
Thank you, Ibrahim. Thank you, Mohammed, for your very interesting tutorial, and also for keeping to the time that we have allocated. So let me now thank the people that have posed questions. I will pass you the questions one by one. I'll start from the last one that just arrived. what if you have to connect temporal data with spatial data? How would you deal with that?
Yeah, so I can talk about this. Yes, that's an interesting. We try to solve the spatial part first. We did not look at the temporal part, and I'm not aware that there are many things there. I think it's our first step is to look for the spatial stuff, but definitely temporal is next. And I would say that it's not going to be a trivial extension to go from spatial to spatial temporal.
Okay, so you will follow the traditional approach, let's say, Mohammed, right?
Yes. Yes.
Okay.
We
Okay.
had a lot of work in spatial big data, and then we moved to spatial temporal. Yeah, it's not a trivial extension, and there's not much work there. And I think we're starting to scratch the surface of doing things with machine learning with spatial data. And yes, we're going to look at temporal next. Yes.
Okay. The next question is the following. We normally think deep learning models like CNN and LSTM, we normally think that they can learn and utilize spatial/temporal information automatically. Do we still need to extend these models to spatial data? If yes, what type of extensions are needed?
Yeah, I can answer this or elaborate about this question. So basically, yeah, we definitely convolutional neural network and this kind of like specifically the convolutional based approaches are specifically designed to capture the locality, and they are introduced for this like reason in the image analysis at the first place. But as we have shown, for example, in traffic prediction, we need to design a specific filter or like specific way of like connecting the information between different nodes based on route segments, for example, or for example, like in graphical convolution, we can take into account the neighborhood information. So it's not like the traditional convolutional neural network. You need to do some extensions based on the spatial constraint that you are specifying. For example, for the traffic prediction, or for example, in the routing, you have some constraints that you need to extend the filters that you have in the convolutional neural network to be more efficient in these cases. And in this kind of papers that we have highlighted in the tutorial, they have done this. Like they started with doing the traditional convolutional neural network, for example, with its default spatial filters, and they found that it's still having some limitations. And then they design more filters or like more specific things to do this.
I can add to this here, generally speaking, not only to CNN, the ability of utilizing spatial or temporal information has different meanings here. One meaning, for example, is that I'm going to support it from the data types only. So I will just add spatial types, and that's basically my support for spatial data. That's not everything. Another meaning is that, oh, I'm going to consider the locality between points, either as a time series, for example, that is a temporal locality, or as points neighborhood to each other. And then, because I'm considering locality, that's everything. No, that's not everything. There's deep in the system yet that these points that are localized need to be stored together and indexed in a way that provide more efficient. So there are always techniques that utilize spatial or temporal information at one level of the stack. But what we are calling for is that you may need to think of the whole stack together. Yes.
Okay. Thank you, Mohammed and Ibrahim. Let me check here the questions again. An interesting question that just arrived is the following. Have you faced problems trying to find big spatial data sets for applications related to traffic prediction and trajectories? If so, how have you dealt with them?
Okay, so there are some available datasets online. I agree it's not large. It's, working in QCRI in Qatar, I'm lucky to have access to all taxi data in Qatar. We have access to them as a live stream. So I can get all the data coming from all taxis, and that's really big data. and very valuable data. I know that other people in other small countries like Qatar have some similar access. In US, you don't have this. There was the public data set, New York taxi data, but that's not really as large as it should be. Yeah.
Okay, thank you, Mohammed. Another question is the following. What new challenges do machine learning and deep learning algorithms raise to spatial data processing and access methods?
Yeah, so basically, what I found in the literature survey here that we have done for this tutorial, that so many approaches like machine learning and deep learning approaches are used to enhance the performance for spatial data analysis operations, not for the spatial data access method or spatial data management operations. And the only thing that connects between the data accessing or data partitioning and the machine learning approach is what we talked about, for example, in the first quarter, the quad-tree partitioning thing for convolutional neural networks. So now they are using these access methods for improving the performance of the machine learning or deep learning approach. But I'm not aware of anything till now using the machine learning to fundamentally improve the access methods that we have in the spatial data. So of course, there's some recent work on learning multi-dimensional indices, for example, in Sigma, or trying to borrow the same ideas that we haven't learned indices also in the spatial data, but still not many approaches are now beating the current state-of-the-art approach. We don't know exactly if they are so much efficient or not. We're still under investigation. So it's not so many approaches about this now existing.
So if you look at the recent SIGMOD VICD, I mean, the ones that this year and last year, there's at least 5 or 6 papers talking about auto learning index for spatial data. Following the paper about learning index, like the B3 learning index, people have followed with the spatial data. But to me, that's one trial to mimic something that happened for learning index, but not as a system or not going through the whole stack. There are projects now, and I think Ibrahim is participating in one of these projects, is how to have a whole stack of machine learning to fit databases or systems for machine learning. This is missing in spatial data.
Okay, thank you both. There are 2 more questions that I would like you to consider. The first question is whether you could talk a little bit about the spatial factor graph that you mentioned in one of your slides. I suppose you will have to go back to that.
Yeah, so basically, I don't know if the time will allow us to give more details about this or not, but basically in the spatial factor graph, what we mean is that it's a variation of the factor graph. So factor graph is a way of constructing the relation between random variables that we want to apply any learning and inference operations on them. And the way they are using here, that they are not considering the spatial correlation between the different variables. So if you have 2 logical variables, you can represent them using the factor graph. But you don't have any way for the vanilla factor graph or the traditional factor graph to represent the spatial correlation between variables. What we want to do in this, or what we are proposing in the spatial factor graph, that even if you have these 2 variables connected logically, they also can have some spatial correlation between them, and we can add some spatial factors specifically designed to capture this spatial semantic. So that's what we mean by spatial factor graph. And if the listener is interested in more details about this, we're going to talk about this also in our session on Thursday for the details about SEA. So we're going to describe in detail how the spatial factor graph looks like.
Okay, thank you, Ibrahim. And one more question, which is probably related to SEA as well. In the knowledge extraction example with which you started the presentation, Mohammed, I suppose, started the presentation. You said that Deep Dive cannot handle the spatial questions because they don't have binary answers. But the statements P1 and P2 that you showed were about education level and crime rate, which also don't seem to have binary answers. Can you expand on that a little bit?
They actually have binary answers, because the predict one says that an education has high crime rate, and this is either 1 or 0, whether it has high crime rate or not. And the second one was that the two cities are have the same education level, and that's also the answer to it is either 1 or 0. And maybe here the interpretation of have the same education level doesn't have to be 0.7, 0.5, like say exact, maybe within some factor. The answer here is 1 or 0. And then when we add the spatial rule, like two cities are within 80 miles, that has 1 0. So in fact, the predicates were binary.
Okay, okay. Thank you for answering this, Mohammed, as well. So let me close with the last question that we have, which is the following. How can causality be handled between different spatial data sets? For example, taxi data and weather data, particularly with tools such as Flash and Spatial.
So I can talk for Flash, for example. So we have implemented the spatial Bayesian network, for example, like probabilistic graphical model for handling the causality itself. So Bayesian network itself is handling is a graphical model to handle the causality, and also we implemented a spatial Bayesian network which is handling also the spatial correlation and causality at the same time. So it's a very well-known probabilistic graphical model, and what we have done in Flash here that we just implemented the approach, the traditional approach, but now in a scalable way. So as a short answer here, causality can be handled with an approach like spatial Bayesian network. And by using Flash, we can have a scalable approach like this. I'm not sure if Spatial can be used to implement this approach or not. I'm not aware of any probabilistic graphical model is implemented using Spatial, but I need to double check this. Yeah.
Okay, thank you, Ibrahim. I promised that this would be the last question, but there is one more which is really interesting, and I would like you to consider this as well. Could you elaborate a bit more on both future research directions and challenges related to both big spatial data and machine learning?
Yeah, okay. So I think it was the main part of the tutorial is putting this kind of classification of spatial and non-spatial data. Once you start thinking that spatial data is different than non-spatial data, this opens a huge, open a lot of directions for future research things. For example, and I usually take it from the application side. There are a lot of application side in spatial data that you can think of using machine learning for them. And from the other side, which is a practice, honestly, I always do with my own PhD student, is that we get a system that is running already, a system that is very well used, and just try using it in spatial data. Most likely, you will find that the answer is not satisfactory, because usually the system designers usually think of spatial data as an afterthought problem. That's usually open a lot of things here. Another thing is, like one asked before, the temporal part is really missing. It's not in the picture yet. So this could be immediate future things.
And if I can add to what you answered, Mohammed, and then you also know how to write the paper, right? Because you start by saying what the problem is with the current system, and then how you solved it. So it's a really exactly. Nice way to look at that. Okay, okay. So let me.
Yeah, this was really an excellent tutorial. I was here for most of it, and I found it very useful. Thank you very much.
Thank you, Wafa.
Thank you.
And on behalf of the organizers, I would also like to thank Professor Manolis Koubarakis, who is himself an expert in this area, for expertly running the session.
Thank you.
Thank you. So allow me to thank Mohammed and Ibrahim one more we can clap electronically or in any other way. We can stop here. I would like to thank the people that asked the questions and all the other participants as well. Now there is a break, and then we go on to the second keynote.
Right, and
So
that will be in the same room, right? The webinar room, the second keynote. Right, it's going to be in the webinar room, I believe. Yeah. Thank you.
Thank you.
Thank you.
So the student worker, I think we need to stop sharing the screen, right? So that, right. Okay, thank you.